Tesla's factories are high-speed and all-electric powerhouses, redefining how cars are built. From massive Giga presses shaping entire frames in seconds to precision robots installing batteries and software systems, every Tesla is engineered with ruthless efficiency. In this video, we take you inside the cutting-edge process that brings these revolutionary vehicles to life. The production of a Tesla vehicle begins long before any car takes shape on the assembly line. Deep within the vast expanse of a Tesla Gigafactory, a meticulously orchestrated sequence of processes brings together raw materials, robotics, and human ingenuity to transform aluminum, lithium, silicon, and countless other elements into one of the most advanced electric vehicles on the planet. From the first bolt of sheet metal to the final pixel on the touchscreen interface, every component is born of a vision rooted in automation, precision, and sustainability. We begin with the raw materials that will ultimately form the structural skeleton of the car. Aluminum coils. These massive, industrial-grade aluminum rolls are delivered to the stamping facility in pre-cut widths and are carefully inspected for thickness consistency, surface finish, and chemical composition. Tesla predominantly uses high-strength aluminum alloys for many of its structural components due to their lightweight yet durable properties. These alloys are crucial to achieving Tesla's performance goals without sacrificing efficiency or safety. As each coil is unspooled, it is fed into a massive blanking press, a machine capable of cutting large sheets into specific dimensions called blanks. These blanks, often the size of a car door or hood, are prepped for the stamping process, where one of the most visually dramatic parts of the car's creation takes place. The stamping area, often housed in its own building due to the sheer vibration and noise, is where enormous dies, precision-engineered molds weighing several tons, shape these blanks into panels that will form the body-in-white structure of the car. Each die is lowered into a stamping press, often a servo-driven press with forces exceeding 5,000 tons. These machines exert immense pressure in milliseconds, forming the aluminum blank into complex geometries. Multiple stages of stamping may be needed for a single panel, including draw, trim, pierce, and flange operations. After stamping, robotic arms lift and transfer the formed panels onto conveyor belts, directing them to a quality inspection zone where laser scanners and human inspectors check for warping, stress marks, or micro cracks. Any deviation from tolerance can compromise fit or function and is promptly rejected or reworked. While the body panels are being shaped, another process begins deep inside the battery cell manufacturing area. Tesla, being vertically integrated, produces many of its own lithium-ion battery cells. Raw materials such as nickel, cobalt, manganese, and lithium carbonate are transported into specialized mixing tanks where they undergo slurry formation. These slurries are spread onto copper and aluminum foils, which are then dried in a vacuum oven to form electrodes. Once the electrodes are prepared, they are calendared, flattened to precise thicknesses, and wound or stacked into cylindrical, pouch, or prismatic cells depending on the vehicle model. Each cell is filled with electrolyte solution and hermetically sealed in a dry room to prevent moisture contamination, which could compromise safety or performance. These cells are then loaded into battery modules using robotic pick-and-place arms, which align and connect the terminals with extreme accuracy. The modules are assembled into packs, which include integrated cooling channels, structural support, and electronic control units. These battery packs will eventually be installed into the vehicle's underbody, providing both power and structural rigidity. Back in the body shop, the stamped aluminum panels are robotically welded and riveted together to form the body in white, the term for the car's skeletal shell before any paint or interior components are added. Tesla employs a combination of laser welding, spot welding, and structural adhesive bonding to fuse panels together with minimal distortion and maximum strength. Hundreds of robotic arms suspended from overhead gantries work in synchronized motion, welding, clamping, positioning, all choreographed with software that can adjust in real time based on tolerances and feedback. Laser scanners constantly monitor joint integrity and positional accuracy, ensuring that each weld is correctly formed and precisely located. The body in white at this stage is a gleaming raw aluminum shell, unpainted but fully formed, with all major exterior panels in place, including doors, hoods, and trunk lids, which are often removed and processed separately for better access and quality control. The next destination for the body is the paint shop, one of the most complex and environmentally controlled areas of the entire factory. Before painting can begin, the aluminum body must undergo a chemical pre-treatment process that removes oils, residues, and impurities. This is achieved by submerging the body in a series of baths, alkaline cleaners, deionized water rinses, and ultimately a zirconium or phosphate-based conversion coating that promotes adhesion and corrosion resistance. After drying in an oven to eliminate residual moisture, the body moves into the electrocoating tank, or e-coat stage. Here, the entire shell is submerged in a bath of electrically charged paint particles, which uniformly coat every crevice and interior cavity, ensuring anti-corrosion protection even in areas never visible to the customer. The body is then baked in a curing oven to harden the coating and prepare it for the next layers of paint. The painting process involves multiple coats: primer, base coat, and clear coat. Each coat is applied in sealed spray booths using high-precision atomizing robots, which follow programmed trajectories to ensure even coverage. Advanced electrostatic spray techniques are used to minimize overspray and improve efficiency. After each coat, the vehicle passes through a series of flash and bake ovens to dry and cure the paint, creating the high-gloss finish Tesla vehicles are known for. Once painting is complete, the body heads to the general assembly area, where it begins to transform from an empty shell into a fully operational vehicle. But before any parts are installed, the body undergoes another round of rigorous inspections. Laser alignment systems, gap and flush measuring tools, and robotic probes verify dimensional consistency across every surface. Any discrepancies are flagged and corrected before proceeding. Simultaneously, thousands of components are arriving from various sub-assembly lines and suppliers, including the interior trim, seats, dashboards, glass, wiring harnesses, and powertrain modules. These parts are delivered using automated guided vehicles, AGVs, that navigate the factory floor using embedded magnetic strips or LiDAR-based systems, ensuring just-in-time delivery with minimal human handling. The interior assembly begins with the installation of wiring harnesses, which are laid throughout the vehicle like a nervous system. These harnesses, containing kilometers of wire, are clipped into designated paths along the floor, pillars, and roof. Robots and human technicians work together, ensuring connectors are correctly routed and terminals are securely fastened. Next, the HVAC components, dashboard structure, and infotainment systems are installed, followed by airbags, sound insulation, and seat frames. At each step, torque-controlled tools and digital confirmation systems ensure that every fastener meets the required specification. The vehicle's panoramic glass roof, a signature element of Tesla's design language, is then lowered into place using vacuum suction lifters and laser-guided alignment tools. A two-part adhesive is applied by robotic nozzles to create a watertight seal. The doors, previously processed separately, are reattached and calibrated to ensure perfect alignment and smooth operation. Tesla's frameless door design and automatic opening features require particularly tight tolerances and sensor calibration. With the interior taking shape, the vehicle proceeds to powertrain integration, where the battery pack, assembled and tested in a parallel process, is lifted by robotic jigs and bolted into the vehicle's underbody using a sequence of torque-controlled actuators. The drive units, whether dual or tri-motor, are then installed onto the front and rear subframes, connected via suspension arms and motor mounts that are pre-aligned using precision fixtures. With the battery pack securely mounted and the drive units in position, the vehicle is now ready to undergo one of the most critical transitions in the entire manufacturing process: electrical and software activation. While the car may appear nearly complete, it is still lifeless. No lights, no screen activity, no sensor communication. This stage, often referred to as initialization, is where the vehicle essentially takes its first breath. A technician connects a diagnostic interface to the vehicle's central computer, usually via a secure data port under the dash, and uploads the foundational firmware that activates the vehicle's electronic control units, or ECUs. Each Tesla contains dozens of ECUs distributed throughout the chassis, responsible for everything from motor control to autopilot systems, battery thermal regulation, infotainment, and safety monitoring. Tesla's approach to software architecture is notably centralized compared to traditional automakers. Instead of relying on fragmented systems developed by various suppliers, Tesla has developed an in-house software stack that enables over-the-air updates, real-time diagnostics, and direct integration between mechanical systems and the vehicle's neural net. Once the firmware is loaded, a cascade of subsystems begins to power on. The touchscreen illuminates for the first time. The instrument cluster boots up. Cameras begin streaming to internal diagnostics. Every sensor, switch, and relay goes through a self-check process that verifies communication with the vehicle's central gateway. Any issues, such as a disconnected wire, a miscalibrated radar unit, or a sensor failure, are immediately logged for remediation. At this stage, even something as minor as a single LED malfunction will halt the progression until it's resolved. Next, attention turns to calibrating the advanced driver assistance systems. Tesla's autopilot suite relies heavily on an array of forward, rear, and side-facing cameras, ultrasonic sensors, and radar or LiDAR, depending on the model and hardware iteration. These units must be precisely aligned within the bodywork to ensure accurate environmental perception. Calibration is not just mechanical, but also algorithmic. As the vehicle is rolled into a controlled calibration zone, a series of reference panels, patterns, and 3D markers are placed around the car. Cameras are activated, and software compares live imaging data against known coordinates to fine-tune the visual input. The system will not pass if even a single camera is slightly skewed or obstructed. Following this, the wheels and tires are mounted, another process where automation and precision intersect. Each wheel assembly, comprising the tire, alloy rim, TPMS sensor, and balancing weights, is prepared in an adjacent sub-assembly cell. Robotic arms select the correct wheel variant depending on trim level and mount it onto the vehicle's wheel hub using torque-monitored tools. Once installed, the wheels are not yet fully ready for the road. They must be aligned. Wheel alignment takes place on a dedicated platform, where laser or camera-based alignment tools measure caster, camber, and toe angles in real time. Adjustments are made on the spot using robotic wrenches that turn suspension bolts until readings fall within micrometer level tolerances. Proper alignment is vital, not only for performance and safety, but also for autopilot accuracy, as steering bias or drift could interfere with the vehicle's self-driving capabilities. Now we arrive at one of the most impressive parts of Tesla's assembly process: final assembly verification and end-of-line testing. This begins with a full-body water intrusion test. The completed vehicle is driven, or in some cases, automatically transported, into a sealed chamber known as the water test booth. High-pressure nozzles blast the car from all directions, simulating rain, puddle splashes, and pressure washing. Sensors inside the cabin monitor for even the slightest moisture intrusion. Any leak, even a trace around the door seals or underbody joints, results in a stop and targeted repair. Once the vehicle passes the water test, it moves into dynamic testing. But before that can begin, it must first pass a rolling road diagnostic check. The vehicle is positioned on a set of rollers that simulate driving conditions. Here, Tesla technicians run through a wide range of operational checks. Motor response is tested across a variety of simulated terrain profiles. Regenerative braking systems are evaluated to confirm energy recovery rates match expected values. HVAC systems are activated to check for proper airflow, temperature regulation, and acoustic performance. Inside the cabin, the touchscreen interface undergoes a systems integrity test. Each menu, function, and button is activated in sequence. The infotainment system is tested for connectivity to Tesla's software servers. Navigation modules are initialized. Bluetooth and Wi-Fi antennas are pinged. Microphones and speakers are checked for distortion or static. The cabin camera, located near the rearview mirror, is tested for focus and response to light changes. The glove box, front latch, trunk motors, and window regulators are also checked for proper operation and speed. After static diagnostics, the vehicle is finally ready for its low-speed dynamic test. On-site test tracks, usually located adjacent to or within the Gigafactory premises, allow each vehicle to undergo a short but comprehensive road test. The driver is usually a trained Tesla technician who runs the car through a prescribed routine: acceleration from 0 to moderate speeds, emergency braking, tight cornering, and high-speed lane changes. This test evaluates suspension response, noise levels, steering feel, and drivetrain behavior under real load conditions. The vehicle's software continues to log performance data throughout the drive, flagging any anomalies. After returning from the test track, the car enters the final visual inspection area. Here, a team of human inspectors, armed with light panels, bore scopes, and digital checklists, reviews every visible surface inside and out. Paint quality is scrutinized for orange peel texture, swirl marks, or dust nibs. Panel gaps are measured by hand and with laser gauges. The interior is inspected for material alignment, stitching accuracy, and uniform texture. Every single button, vent, trim piece, and fixture is physically touched and verified. If the vehicle passes this multi-layered gauntlet of inspections, it moves into what's known as pack out, the final preparation area before shipment. Here, the car receives its VIN label, ownership documentation, and destination configuration. This is where region-specific software settings, navigation maps, and language preferences are loaded. The final battery charge is administered, usually to around 90%, before the vehicle is powered down and prepared for transport. Each Tesla is now ready to leave the factory, but even this step is a study in logistical precision. Automated systems coordinate the movement of completed vehicles from the final inspection bay to outbound logistics. Depending on destination, the vehicle may be loaded onto a covered rail car, placed into a secure car carrier, or transferred to a nearby delivery hub. RFID tags embedded in the vehicle identify it to tracking systems that monitor its journey to the customer. It is important to note that Tesla's manufacturing ethos is grounded in continuous improvement. Unlike traditional automakers that rely on annual model cycles, Tesla frequently changes its assembly lines in real time, updating hardware or processes based on production learnings, user feedback, and software improvements. This philosophy means that even within the same week, two identical models may have subtle differences in componentry, firmware version, or assembly methods. These continuous upgrades are made possible by Tesla's heavy reliance on vertical integration and factory-level data analytics. Every torque wrench, sensor, robot, and diagnostic station feeds data into a centralized factory control system. Engineers analyze this data daily, making adjustments to improve efficiency, reduce rework rates, and enhance vehicle quality. This feedback loop between digital twin modeling, live production, and field performance is one of the reasons Tesla has been able to scale quickly while maintaining product innovation. With the vehicle now fully assembled, inspected, and approved, it embarks on the final leg of its journey: delivery to the customer. Whether arriving at a showroom, a regional distribution center, or directly to a driveway via Tesla's direct delivery program, the finished product represents not just a vehicle, but the culmination of thousands of interconnected systems working in harmony, each with millisecond-level precision, each tuned for performance, safety, and the future of mobility. Once a Tesla vehicle has cleared its final inspection and receives its shipment authorization, the journey from the Gigafactory to the customer begins. Unlike conventional auto manufacturers, which often rely on third-party dealership networks and extensive warehousing chains, Tesla's direct-to-consumer delivery model has radically simplified and streamlined this phase. Yet, behind that apparent simplicity lies a highly coordinated logistical infrastructure, optimized to handle the massive volume of vehicles produced daily across multiple global factories. At this stage, the vehicle is routed into a specialized outbound logistics yard, a designated section of the Gigafactory site, or an adjoining facility engineered specifically for the staging, sequencing, and transportation of finished vehicles. Each car is tagged with a digital shipping label that contains its vehicle identification number, model variant, color, wheel configuration, destination, and special instructions such as left-hand versus right-hand drive. This digital manifest is cross-referenced with Tesla's centralized logistics control software, ensuring that each car is placed into the correct regional batch for dispatch. Automated tug vehicles, similar to those used in airport ground operations, tow trailers of Tesla vehicles into position. If the vehicle is destined for domestic delivery, it is typically loaded onto a car carrier truck designed to hold 7 to 10 units. These carriers are scheduled to depart in tightly timed intervals, with software routing each truck for the most efficient delivery path based on real-time traffic, weather, and destination inventory levels. For international shipments, the process shifts slightly. Vehicles bound for overseas markets are loaded onto rail cars or container haulers that transport them to port facilities. At the port, the vehicles are driven onto roll-on/roll-off ships, a type of cargo vessel with built-in ramps and internal decks specifically designed for transporting cars. Each Tesla is parked and secured inside the vessel, often alongside other vehicles of the same batch, in a configuration that minimizes offloading time upon arrival. Throughout this journey, every vehicle remains digitally visible to Tesla's logistics team. GPS tags, onboard cellular connectivity, and carrier integration systems allow real-time tracking from the moment the vehicle leaves the plant to the moment it is delivered to the end customer. This level of transparency enables Tesla to forecast delivery windows with a high degree of accuracy and proactively resolve issues like weather delays or customs bottlenecks. Meanwhile, Tesla's delivery centers and service hubs are preparing to receive the vehicles. These locations, often converted warehouse spaces or minimalist showrooms, act as regional fulfillment points. Upon arrival, each vehicle undergoes a final pre-delivery inspection. This includes checking tire pressures, topping off windshield washer fluid, confirming that the software version is current, and ensuring the paint and interior remain in pristine condition. The protective coverings applied during shipment, such as plastic seat covers and foam door guards, are removed, and the car is detailed for presentation. If a customer has opted for Tesla's home delivery option, the vehicle may be dispatched from the delivery center directly to the buyer's driveway using either a flatbed or a mobile technician. Tesla's minimalist approach to delivery day often involves minimal paperwork, since much of the ownership transfer process is handled digitally ahead of time. Customers sign final documents electronically, receive a tutorial on using their new vehicle via the in-car interface or mobile app, and are given access to Tesla's expansive digital support ecosystem. But delivery is not the end of the story. It's merely the handoff point between manufacturing and long-term ownership. Tesla's commitment to post-production support is tightly integrated into its digital platform. The same software and hardware systems that facilitated the car's birth on the factory floor now serve as tools for its ongoing evolution. Over-the-air updates are one of the most defining characteristics of the Tesla ownership experience, and they depend on a robust ecosystem of remote diagnostics, data collection, and machine learning feedback loops. Every Tesla on the road constantly reports anonymized performance data back to Tesla's servers. This includes battery health, motor efficiency, navigation anomalies, autopilot behavior, sensor readings, and even software bugs. Engineers at Tesla's headquarters use this data to refine algorithms, push updates to correct inefficiencies, and enhance safety features, all without the owner needing to visit a service center. This dynamic software lifecycle, enabled by the tightly coupled manufacturing and software teams, makes Tesla vehicles unique in their ability to improve long after leaving the factory. Meanwhile, Tesla's service infrastructure continues to grow alongside its production volume. Instead of relying entirely on traditional service centers, Tesla employs a mobile service strategy wherever possible. These service vans are equipped with diagnostic tools, replacement parts, and certified technicians who can perform a wide range of repairs or updates at the customer's location. The ability to diagnose and even preemptively fix issues before they affect the driver is rooted in the precision and data fidelity achieved during the original manufacturing process. Looking back toward the factory, it's important to understand how Tesla's architectural philosophy supports this entire life cycle. Every Gigafactory is designed not just to build vehicles, but to serve as a data hub, a testing ground, and a self-improving machine. These plants are built with flexibility in mind, using modular assembly lines that can be reconfigured on the fly. Instead of fixed conveyor belts, Tesla often uses autonomous mobile robots and smart material flow systems that can reroute components or vehicles as production needs change. The Gigafactory floor is not one continuous line, but a series of interconnected stations. Each one is equipped with sensors, machine vision, and feedback modules that report into a central factory operating system. This system not only tracks current production metrics, but also simulates process optimizations. For example, if a torque reading at a robotic arm consistently falls within the low-end threshold, engineers can be alerted and update the robot's behavior before a quality deviation even occurs. This predictive control approach reduces downtime and increases first-pass yield, meaning more vehicles pass inspection on the first try without needing rework. Vertical integration plays a critical role in making this system work. Tesla doesn't just assemble parts, it manufactures many of them. From battery cells to electric motors, from infotainment chips to firmware code, Tesla has brought traditionally outsourced operations in-house. This reduces dependency on suppliers, shortens feedback loops, and allows the company to innovate rapidly. For instance, if a new battery chemistry is developed in Tesla's R&D lab, pilot-scale production can begin almost immediately within a section of the existing Gigafactory, without the need for third-party approval or infrastructure overhaul. Even Tesla's supply chain reflects this philosophy of speed, control, and adaptability. Critical materials like lithium, nickel, and cobalt are sourced through long-term contracts with mining operations. And in some cases, Tesla has invested directly in extraction or refinement operations. These materials are routed directly to gigafactories or regional production hubs, bypassing many of the bottlenecks that affect traditional automakers who rely on complex supplier tiers and international freight forwarding. This system is further enhanced by Tesla's real-time digital twin architecture, a virtual replica of the entire manufacturing process. Every machine, part, and process is mirrored in a digital environment that can simulate disruptions, forecast efficiency gains, and run hypothetical scenarios. Want to test how a new weld technique might affect throughput? The digital twin can simulate that change in minutes, allowing engineers to make data-backed decisions that translate directly into physical adjustments. Through all of these layers, physical infrastructure, software integration, vertical manufacturing, and delivery logistics, Tesla has redefined what modern automotive production looks like. It's not just about building cars, it's about building a system that builds itself smarter with every iteration. Every vehicle produced feeds data back into this system. Every manufacturing anomaly becomes a learning opportunity. Every software update enhances not just the product, but the factory's ability to produce the next one even better. What this means is that the Gigafactory isn't a static building. It's a living organism, a self-correcting, self-improving entity designed not only to produce cars, but to redefine what a car even is in the age of autonomy, electrification, and artificial intelligence. And at the center of this vision lies a carefully choreographed dance of machinery, people, data, and innovation, all working in harmony to create not just a vehicle, but a new standard for the global auto industry. Inside a Tesla Gigafactory, perhaps the most mesmerizing and defining visual is the near-symphonic choreography of robots working in harmony. Tesla employs tens of thousands of industrial robots across its global facilities, many sourced from automation giants like Kuka and Fanuc, and many others developed in-house. But these aren't the slow, single-arm welders of traditional auto plants. These are high-speed, multi-axis machines operating in tightly coordinated clusters that resemble mechanical dance troupes, fast, precise, and relentlessly efficient. The bulk of these robots are deployed in the body shop, where raw stamped panels are joined to form the body in white. Here, multiple robot arms work within inches of one another, one positioning a panel, another applying structural adhesive, and a third completing a weld, without ever colliding. This level of spatial awareness is made possible by a digital supervisory system that orchestrates each motion path in microseconds. Each robot is fitted with a suite of sensors, including force feedback, proximity detectors, and sometimes even cameras, allowing them to adapt slightly if a panel is marginally misaligned or a weld point needs micro adjustment. In many production cells, Tesla has implemented what are known as friction stir welding units, robots capable of joining aluminum panels without melting them. This technique, originally developed for aerospace manufacturing, uses a high-speed rotating tool that generates frictional heat to soften and fuse materials without introducing impurities or thermal distortion. It results in stronger joints and is especially effective for joining thick battery pack casings or high-stress structural nodes. But Tesla's automation does not end at the mechanical level. Surrounding the physical robots is a vast digital control infrastructure powered by machine learning algorithms that analyze every torque value, weld voltage, and robot movement. These systems compare every single action against historical data to identify patterns that may indicate future faults. For example, if a particular welding arm shows a slight uptick in motion latency or current draw, the system can schedule predictive maintenance before a full failure occurs. This predictive maintenance loop dramatically increases uptime and reduces unexpected halts in the production line. Complementing this robotic workforce is a carefully integrated human team. Contrary to the misconception that gigafactories are purely robotic, Tesla maintains a robust human workforce in areas where judgment, dexterity, or problem solving are still superior to automation. For instance, interior trim installation, particularly tasks involving soft materials like Alcantara, stitched leather, or delicate wiring, still relies on trained technicians who can feel for correct tension, align materials by eye, and make subtle corrections during fitment. Human workers are also essential during final inspection, dynamic testing, and exception handling. If a part doesn't meet specifications, or if a software glitch prevents a subsystem from booting, it's often a human specialist who diagnoses and resolves the issue. These employees are equipped with digital tablets linked to Tesla's internal manufacturing cloud. They receive live data feeds from the vehicle's onboard sensors and can pull up schematics, tolerances, and previous production history in seconds. Every fix they apply, every note they enter, becomes part of that car's digital footprint, a log that follows it forever, even into post-sale diagnostics. Tesla's approach to worker efficiency is also shaped by ergonomic engineering and cognitive load optimization. Workstations are designed to reduce repetitive strain injuries with tool arms that balance heavy equipment and lift assists for placing components. Augmented reality overlays are sometimes used during training phases, projecting digital guides onto surfaces to help new employees understand complex assemblies. Rotational schedules ensure workers shift between physically demanding tasks and more routine duties, helping prevent fatigue-related errors. As we dig deeper into the brain of the Gigafactory, we arrive at what is perhaps Tesla's greatest long-term differentiator: the use of artificial intelligence, not just in the vehicles, but within the factory itself. Tesla doesn't merely automate individual machines, it trains its factories to optimize themselves. This is achieved through a combination of real-time data ingestion, cloud-based analytics, and reinforcement learning loops. Let's take an example from the paint shop. Traditionally, robots follow predefined spray paths based on CAD data. However, Tesla trains its painting robots using vision-based systems that analyze each body shell in real time for curvature, panel orientation, and gap uniformity. This data informs dynamic adjustments to spray trajectory, nozzle pressure, and stroke timing. The result is more uniform coating, fewer touch-ups, and improved long-term finish durability. Or consider battery pack assembly. Each cell inserted into a module is monitored for voltage, internal resistance, and capacitance. Tesla uses this data to build a profile of every module's thermal characteristics. If a pattern of abnormal cell degradation is observed in the field, engineers can trace it back to the exact production batch, process variables, or even environmental conditions at the time of assembly. This data loop enables retroactive improvements to manufacturing conditions and helps refine pack longevity models for future software updates. One of the more futuristic systems Tesla is rolling out across its newer Gigafactories involves swarm intelligence for material transport. Rather than fixed conveyor systems, Tesla uses fleets of autonomous mobile robots that navigate the factory floor using SLAM algorithms. These robots aren't programmed with fixed paths. They learn optimal routes in real time, adapt to obstacles, and communicate with one another to avoid collisions or bottlenecks. This approach allows the factory layout to be more modular and reconfigurable, supporting agile production and faster adaptation to new models or variants. Equally fascinating is Tesla's use of simulation environments for factory operations. Entire sections of the Gigafactory are mirrored in a digital twin, an exact 3D replica of the physical space and its processes. Engineers can run simulations to test new workflows, evaluate machinery upgrades, or even plan how to integrate a new vehicle platform without ever disrupting the live production line. If a simulated robot collision is detected, the system can suggest path modifications or sequence changes before real-world implementation. This same philosophy extends to Tesla's use of custom silicon chips. While best known for its full self-driving computer, Tesla also designs specialized hardware for internal factory use. These include image recognition chips optimized for high-speed defect detection, edge computing units for data processing at the machine level, and embedded control systems that allow more precise energy regulation in welding and curing ovens. This level of hardware customization provides Tesla with granular control over quality, energy efficiency, and process speed. Another compelling layer of Tesla's factory evolution involves environmental engineering. Every Gigafactory is designed with sustainability as a core tenet. Rooftop solar arrays, on-site water recycling systems, and battery-powered internal logistics vehicles are just some of the components contributing to closed-loop manufacturing. The energy used to produce each Tesla vehicle is increasingly being sourced from renewable systems within the facility itself, dramatically lowering life-cycle carbon emissions. Tesla's focus on vertical integration again becomes critical here. When energy systems, battery chemistry, robotics, and software all originate from the same corporate ecosystem, coordination becomes exponentially easier. Design tweaks to the battery casing, for example, can immediately inform changes to the casting molds, welding fixtures, or software-based thermal models, without the friction of cross-company coordination. Perhaps the most emblematic symbol of this holistic integration is Tesla's Giga casting machines. These are among the most powerful aluminum die casting machines in the world, capable of creating entire underbody sections as a single solid piece. These machines, designed in partnership with Adidra, reduce the number of parts in the vehicle's chassis from hundreds to just a few, eliminating fasteners, reducing weight, and improving crash performance. Integrating such massive components into the production line requires not just physical reconfiguration, but software integration, supply chain alignment, and real-time QC adaptation, all of which Tesla is uniquely positioned to manage in-house. As we look at the sum of all these systems, robotics, AI, digital twins, human-machine interfaces, gigacasting, and energy-conscious infrastructure, it becomes clear that the Tesla production process is not simply a variation on traditional automotive manufacturing. It is an entirely new operating system for building cars. A platform, not just a plant. A fusion of machine intelligence, predictive analytics, physical innovation, and agile design thinking, all operating under a single cohesive philosophy. The Tesla Gigafactory isn't just where vehicles are built. It's where ideas are born, tested, scaled, and refined in real time. Where the boundary between hardware and software dissolves. Where every sensor, every weld, and every decision feeds back into a growing repository of knowledge that powers the next generation of vehicles, robots, factories, and systems. One of the most disruptive engineering breakthroughs in Tesla's modern manufacturing playbook is the integration of the structural battery pack, a complete rethinking of how the battery, chassis, and underbody of the vehicle work together. In traditional automotive design, the battery pack is a standalone component, an energy container bolted to the car's underbody. But in Tesla's structural pack architecture, pioneered with the 4680 battery format, the battery no longer rides beneath the structure, it becomes the structure. To understand the scale of this shift, we first need to explore the 4680 cell itself. Named for its dimensions, 46mm wide and 80mm tall, the 4680 cylindrical lithium-ion cell represents a significant departure from the older 2170 and 18650 formats. It offers 5 times the energy, 6 times the power, and reduces the cost per kilowatt hour significantly. But it's not just the size that matters, it's how the cells are built and what they enable downstream in manufacturing. Each 4680 cell is designed to support tabless internal architecture. In conventional cells, current must travel through a tab, a narrow conductor that can create resistance and heat. In Tesla's tabless design, the entire edge of the rolled electrode acts as a current collector, enabling more uniform heat distribution and higher current throughput. This drastically reduces internal resistance, improves efficiency during charge and discharge, and simplifies thermal management, a critical benefit when assembling high-density battery modules. These cells are produced in a vertically integrated line that starts with electrode slurry mixing, followed by coating, calendaring, cutting, and winding, all performed under strict environmental control. The wound jelly rolls are inserted into steel canisters, filled with electrolyte, sealed by laser welding, and then aged, tested, and sorted. What's remarkable is that Tesla's battery lines are not just production machines, they are learning machines. Each stage of battery cell production is heavily instrumented, with sensors that track viscosity, coating uniformity, line tension, and thermal behavior. These metrics feed back into AI-driven quality control systems that adapt in real time, reducing scrap rates and improving yield without requiring line shutdowns. Once the cells are complete, they are no longer assembled into modules as in traditional EVs. Instead, Tesla places them directly into the structural battery pack housing, eliminating intermediary module structures. This pack is a part of the vehicle's load-bearing frame, not an add-on. The cells are bonded in place using structural epoxy, and this bonded matrix provides rigidity akin to an aircraft's wing box design, a technique borrowed from aerospace engineering. A critical enabler of this approach is the use of high-performance structural foams and thermal adhesives. These materials serve multiple functions simultaneously. They manage vibration and noise, conduct heat away from the cells to integrated cooling loops, and crucially, form part of the vehicle's crash energy management system. During side or front impacts, the structural battery pack helps distribute forces across a wider area, reducing localized deformation and improving occupant safety. In the Gigafactory, structural pack assembly is a distinct line, physically separate from standard battery operations due to its unique tooling requirements. Cells are loaded into the pack casing using high-speed robotic insertion machines. Adhesive dispensing systems apply precisely metered quantities of two-part epoxy at high pressure. Once cells are in place, the entire structure is cured in massive industrial ovens that bring the adhesive to full mechanical strength. After cooling, the pack undergoes precision machining to create interfaces for the drive unit, seat mounts, and body attachment points. What results is not just a battery, it's a central element of the vehicle's physical frame. The top of the pack often serves as the interior floor of the cabin. The bottom, reinforced by ribbed aluminum or composite materials, acts as the underbody and aerodynamic tray. By combining energy storage, structural support, and crash safety into a single unit, Tesla eliminates dozens of separate components, reducing mass, simplifying manufacturing, and slashing costs. Now, integrate this with another innovation, Giga casting. Tesla's use of giant aluminum die casting machines to form the front and rear underbody sections of its vehicles is nothing short of revolutionary. These Idura Giga press machines, weighing over 400 tons and applying clamping forces in the range of 6,000 to 9,000 tons, can create entire frame sections as a single cast. Instead of welding together hundreds of stamped components, Tesla now forms massive structural elements in one shot, lighter, stiffer, and far faster to produce. When the front and rear castings are combined with the central structural battery pack, Tesla essentially builds the entire underbody of a vehicle using just 3 large parts. These unibody trios replace what was once over 300 parts in older chassis architectures. This not only reduces complexity and assembly time, but also minimizes the number of suppliers, welds, fixtures, and potential quality defects. Each casting is inspected via X-ray and ultrasonic imaging to detect porosity, cracks, or incomplete fills. Any anomalies are rejected and remelted, maintaining a closed-loop aluminum recycling system. This radical simplification also redefines how the rest of the car is built. Traditional automotive factories are organized around a highly linear body-in-white process: frame construction, then floor pan, then underbody integration. Tesla's method is more like assembling a modular aircraft, where large subassemblies are brought together at fewer, more tightly controlled junctions. This allows Tesla to create more compact factories with faster cycle times and fewer workers per unit produced, metrics that directly impact capital efficiency and return on investment. To support these next-generation designs, Tesla continues to invest heavily in materials science research, much of it focused on high-strength aluminum alloys, advanced polymers, and die-casting feedstock refinement. The development of proprietary aluminum alloys that combine excellent flow characteristics in casting with high tensile strength post-treatment is a crucial part of making gigacasting work. These alloys must cool evenly, avoid brittleness, and withstand both crash loads and environmental exposure over time. In parallel, Tesla is exploring dry electrode manufacturing for future battery lines, a technique that eliminates the solvent-heavy coating and drying stages currently used in electrode production. Dry electrodes can be applied directly to the current collector using pressure and heat, significantly reducing energy consumption, production footprint, and cost. This aligns with Tesla's vision for more sustainable, vertically integrated gigafactories, ones that consume fewer resources per gigawatt hour and can be rapidly scaled in new geographies. Indeed, Tesla's goal is not just to build more cars, it's to scale manufacturing like a technology company, not an industrial one. This means shorter ramp-up times, smaller capital expenditures per unit of output, and a globally unified software-hardware stack that can be deployed anywhere in the world with minimal localization. Future gigafactories, like those planned in Mexico and India, are being designed with these structural pack and casting concepts at their core, meaning they won't just produce the next generation of Tesla vehicles, they will be born already optimized for speed, simplicity, and flexibility. This systems thinking extends even further into factory floor layout and material flow logistics. With fewer total parts, Tesla can implement straighter, more continuous material pathways, reducing the need for kitting, buffering, and material staging. Instead of having dozens of sub-assembly lines feeding hundreds of components, Tesla can deliver entire modules, like castings or packs, straight to the marriage station, where the vehicle begins to take its final form. This layout change reduces floor space, lowers error rates, and improves throughput. It also allows for greater software simulation of factory dynamics. When each vehicle only passes through 30 or 40 production cells, rather than 200 or 300, it becomes computationally feasible to simulate the entire factory in real time. AI-based systems can then test flow changes, balance labor loads, and reroute production if a bottleneck emerges, all before any change is implemented on the floor. The result is a self-learning, self-optimizing factory capable of adapting to demand shifts, supplier disruptions, or design updates faster than legacy automakers can retool a single line. All of this innovation, structural batteries, 4,680 cells, gigacasting, and software-first factories converges into a clear strategic objective: build more cars, better and faster, with fewer people and lower capital costs per unit. It's not about squeezing the last drop of efficiency from legacy systems. It's about replacing those systems entirely. And the boldness of that approach is why Tesla's manufacturing story remains one of the most closely watched industrial transformations of the 21st century. The story of the Skoda Octavia begins long before a single bolt is fastened or a robotic arm glides into action. It begins, in fact, with an idea, a blueprint forged in design studios, simulated on computers, and tested in virtual environments by engineers who must balance performance, efficiency, safety, and style. But for our purposes, the journey begins at the factory, where engineering dreams are translated into industrial reality. Welcome to the highly synchronized and precision-driven world of Skoda Octavia production. Every Octavia starts as raw material, high-strength steel coils delivered to the plant by rail or truck, sourced from carefully vetted metallurgical suppliers across Europe. These coils are massive, weighing several tons each, and are stored in a specially climate-controlled steel depot on the factory premises. Before they even reach the production line, each coil is identified with barcodes, batch numbers, and chemical composition data. Technicians conduct tensile strength and thickness tests to ensure the material meets Skoda's exacting standards. Once approved, these steel coils are fed into the blanking line, an automated system that unrolls, flattens, and cuts the steel into large sheet panels. This is no ordinary cutting process. A high-speed hydraulic press slices the sheets using dies that match each specific component, from door frames to hood panels. The accuracy here is down to tenths of a millimeter. Each sheet is then stacked in order, transported by robotic forklifts to the body shop, where one of the most visually captivating segments of production begins. The body shop is a symphony of automation. Over 600 industrial robots, mostly 6-axis KUKA robots, work with millimeter-level accuracy to build what's known as the body in white, the skeletal structure of the Octavia. Here, robotic arms pick up the steel panels and place them into precision jigs. Another set of robots joins them using spot welding. More than 5,000 weld points are applied to a single body shell, each weld carried out in fractions of a second. Sensors within the robots constantly monitor heat, pressure, and positioning to ensure perfect fusion every time. At this point, the vehicle starts to resemble a car, but just barely. The body is incomplete and fragile, still lacking reinforcements, internal frames, and roof components. The roof is attached next, along with the inner structures of the door frames and A-pillars. This structural framing phase is crucial as it determines the vehicle's crashworthiness and rigidity. Skoda uses high-strength boron steel reinforcements in critical areas such as the B-pillar to enhance passenger protection during side impacts. To ensure dimensional accuracy, every fifth body in white is routed to a coordinate measuring cell, an enclosed chamber with laser scanners and mechanical probes that measure thousands of points across the body. Any deviation outside the strict tolerances prompts a quality control response, sometimes resulting in real-time die adjustments or jig calibrations on the production line. With the structural shell now complete, the body is moved via an overhead conveyor system to the next phase, the paint shop. But before any paint can be applied, the shell undergoes one of the most chemically intensive processes in the factory, the pre-treatment line. Here, the body is dipped into a series of 12 to 14 baths, starting with alkaline cleaners that strip oils and residues from the welding process, followed by zinc phosphate baths that apply an anti-corrosion layer at the molecular level. This immersion is done using a massive rotodip system, which rotates the entire body in white 360 degrees in giant tanks, ensuring every surface, cavity, and seam is fully treated. After rinsing and drying, the shell enters the electro-coating tank, where an electrical current is passed through a special primer solution. The car body acts as a cathode, attracting the primer particles, which adhere uniformly even inside tiny crevices. This electrophoretic coating forms the first of several protective paint layers. From here, the body moves into sealed spray booths where automated sprayers apply multiple coats of paint. typically a base coat for color and a clear coat for gloss and UV protection. The environment inside these booths is tightly controlled. Temperature, humidity, and air pressure are constantly monitored to prevent dust intrusion or paint imperfections. Any deviation can lead to paint defects like orange peel or fish eyes, which are not tolerated on the line. Once painted, the shell is moved into a high-temperature oven or curing oven, where it is baked at around 150 to 180 degrees Celsius for up to 30 minutes. This curing process chemically bonds the paint to the metal, hardening it into a resilient shell. After cooling, a small team of human inspectors examines each body under specialized lighting tunnels, checking for the slightest flaws in gloss, color uniformity, or texture. Any imperfection, no matter how small, is flagged, buffed, or resprayed. Next, the painted shell enters what is known as the trim and final assembly area, arguably the most complex and human-intensive part of the production line. It's here that the skeletal shell of the Octavia transforms into a functional vehicle. The doors are removed temporarily and sent down a separate subline for internal fitting. This allows easier access for workers and robotic systems to install key internal components like dashboards, wiring harnesses, HVAC units, and center consoles. The main body, now called the marriage body, proceeds on a conveyor to the cockpit station. Here, large sub-assemblies, pre-assembled in adjacent areas of the factory, are carefully fitted into place. The dashboard unit, including instrument clusters, infotainment systems, and climate controls, is mounted in one seamless motion using a robotic assist arm designed to handle sensitive electronic modules without damaging connectors or wiring. Wiring harnesses, which serve as the car's nervous system, are routed throughout the body with meticulous care. These harnesses contain dozens of bundled cables, each color-coded and tagged for correct routing to lights, sensors, powertrains, and control modules. Workers follow digital torque instructions via handheld screwdrivers with built-in sensors that alert them to any over or under tightening of critical fasteners. Every step is logged digitally to ensure traceability down to the individual component level. At this stage, the car receives its interior features: carpeting, seats, airbags, and insulation. The seats themselves arrive as complete modules, built in a just-in-time fashion by nearby suppliers and delivered to the line by autonomous mobile robots. Each seat is barcoded and matched to the specific configuration of the car: cloth or leather, heated or ventilated, manual or power adjusted, and installed in one swift but carefully measured motion. As the Skoda Octavia's skeletal structure is now fully formed, painted, and partially assembled with its interior trim and wiring infrastructure in place, the process turns toward one of the most crucial phases of all: the marriage of the car body with its drivetrain and chassis. This stage is where the Octavia transitions from a lifeless shell into a machine capable of movement, energy, and direction. The drivetrain, consisting of the engine, transmission, front and rear axles, and various suspension components, is assembled separately in a highly organized and synchronized subline known as the Powertrain line. This area operates like a standalone microfactory, complete with its own logistics network, inspection checkpoints, and robotic assistance. Engines are delivered from Skoda's engine plant, typically either turbocharged TSI petrol or TDI diesel configurations, though plug-in hybrid variants also have their own specialized integration procedures. These engines arrive as complete units, fully tested, barcoded, and preloaded with essential fluids. Upon arrival, the engines are mounted onto steel cradles, also called front-end modules or subframes, where additional components such as radiators, electric fans, intercoolers, and sometimes the front suspension wishbones are attached. At the same time, transmission units, whether manual or DSG dual-clutch gearboxes, are bolted directly onto the engine block. Robotic torque arms perform these operations with absolute consistency, while sensors record every bolt's torque and angle to ensure mechanical integrity. Meanwhile, on the chassis line, rear axle assemblies are prepared in parallel. For models with multi-link rear suspension, this step includes fitting the control arms, coil springs or dampers, rear disc brakes, and sometimes independent electric motors for all-wheel drive variants. These modules are mounted onto jigs and temporarily stored until they're summoned into position by the main assembly control system, which tracks each vehicle's configuration in real time. Now comes the literal marriage of body and chassis, a highly choreographed operation involving synchronized lifts, conveyor positioning, and robotic alignments. The body of the Octavia, suspended overhead by a guided hoist system, is lowered onto the rolling chassis below with astonishing precision. This alignment must match dozens of mounting points simultaneously: engine mounts, subframe bolts, suspension towers, and driveshaft couplings. The hoist slows its descent incrementally, guided by both optical sensors and laser alignment systems. Once body and chassis are joined, a team of skilled technicians manually fastens the major anchor points, assisted by torque-limiting pneumatic tools. These connections are critical as they determine the vehicle's handling, NVH characteristics, and structural behavior under stress. Each bolt's completion is digitally recorded and verified in the manufacturing execution system, creating a digital fingerprint for the vehicle. Following this milestone, the car begins to resemble a finished vehicle. It now moves under its own chassis wheels onto the next phase: wheel mounting and fluid filling. Tires and wheels are mounted using automated stations that retrieve the correct size and style based on the car's build sheet. Steel wheels, alloys, summer or winter tires, depending on market and order. Robotic arms guide the wheels onto the hubs, while nut runners fasten them in a star pattern to ensure balanced torque distribution. With wheels fitted, the vehicle enters a sophisticated fluid station where all operating fluids are automatically filled. These include engine oil, brake fluid, coolant, transmission fluid, and refrigerant for the air conditioning system. Nozzles are inserted into designated ports, and the exact volume is dispensed under pressure control to ensure no air pockets or underfilling. The brake lines and fuel system are pressure tested during this stage for leaks, and any deviation triggers a diagnostic halt. Electrical systems are now connected and initialized. The vehicle receives its battery, alternator links, and fuse box connections. Diagnostic tools plug into the onboard OBD port to initialize and verify all electronic control units, engine ECU, body control module, infotainment systems, safety sensors, and more. This moment is often referred to as the car's first heartbeat, the first time it powers up electronically and is capable of communication and self-diagnosis. It's also now that the vehicle's doors, which were sent down a parallel sub-assembly line earlier, are reattached. During their absence, each door was fitted with inner paneling, window regulators, speakers, insulation, locking mechanisms, and trim. Robotic arms lift the doors back into position and attach them using high-torque fasteners. Workers verify door alignment, shut lines, and hinge tension to ensure smooth operation and flush fitting. Window calibration tools are also used to check automatic up-down functions, pinch protection, and sealing. At this point, the Octavia proceeds to the dynamic calibration area. Although the car is not yet ready for the open road, it undergoes an initial set of tests to calibrate sensors, align components, and validate subsystem communication. A wheel alignment station uses high-precision optical cameras to adjust toe, camber, and caster angles according to factory specs. Headlights are calibrated in beam testing bays, where optical targets are used to adjust the throw, height, and spread of the light. especially critical for models equipped with adaptive matrix LED systems. Next, the car undergoes brake and suspension testing on a rolling test rig. The vehicle is driven onto a large multi-roller dynamometer where the wheels spin under resistance. During this process, technicians activate the braking system, monitor deceleration curves, and verify that ABS and ESC systems respond as programmed. The suspension is also checked for compliance and noise using vertical shakers that simulate uneven road surfaces. Any creaking, excessive travel, or rattling results in an immediate pull for inspection. A particularly fascinating step follows: the water leak test chamber. Every single Octavia is driven into a sealed tunnel where high-pressure water jets blast the entire vehicle from multiple angles. The test simulates intense rain, car washes, and flood-like conditions. Sensors placed inside the cabin, along with absorbent test materials, detect even the slightest intrusion of moisture. This ensures the integrity of window seals, door gaskets, light assemblies, and sunroof drains. Emerging dry and intact from the water test, the Octavia proceeds to the finishing line, where final interior fittings and cosmetic elements are installed. This includes steering wheels, emblems, gear shift knobs, floor mats, decorative trims, and external badges. Infotainment software is uploaded or updated over a secure network, often using factory-wide Wi-Fi protocols. The vehicle's VIN is permanently etched into structural components and logged in the company's global tracking system. One of the last human-centric inspection areas is the quality audit tunnel. Here, specially trained inspectors perform a 360-degree check under high-intensity lighting to detect any aesthetic flaws, paint imperfections, trim misalignments, stitching errors, or even tiny scratches on window glass. They also run functional checks, including horn operation, screen responsiveness, ventilation airflow, mirror adjustability, and seat motor function. Every button, switch, and knob must perform flawlessly. Before the vehicle can be declared finished, it must complete one more critical phase, the road test loop. A selected percentage of vehicles from each production batch, typically 1 in every 20, are driven on a dedicated outdoor or indoor track. This track simulates real-world driving conditions: cobblestones, sharp turns, acceleration zones, and braking areas. Skilled test drivers listen for unusual sounds, assess steering response, and monitor transmission behavior. Advanced onboard diagnostics log performance metrics throughout the test drive. Once approved, the Octavia returns to the factory's logistics area, where it undergoes its final configuration. Region-specific features such as language settings, radio frequencies, emissions labeling, and immobilizer coding are finalized. Vehicles destined for specific markets, Germany, UK, Scandinavia, or overseas, are grouped together and scheduled for shipment. Once a Skoda Octavia rolls off the production line, fully assembled, tested, and approved, it doesn't simply sit idle awaiting its new owner. What follows is an equally critical, meticulously orchestrated process that transitions the finished vehicle from factory floor to dealership showroom. This final stretch of the production journey may not involve welding robots or paint curing ovens, but it requires an intricate ballet of logistics, digital systems, quality assurance, and environmental controls to ensure that each car arrives in pristine condition, configured perfectly for its destination market. The first step begins at the vehicle dispatch yard, a massive, secure expanse typically located adjacent to the main factory grounds. This area operates like an open-air inventory matrix. Rows of finished Octavias, arranged by drivetrain type, paint color, market region, and model variant, are lined up with absolute geometric precision. Each vehicle's location is tagged via RFID or barcode systems and updated in real time into Skoda's global logistics management platform. The platform tracks not only the physical location of each vehicle, but also its production status, destination, and shipping schedule. Before any vehicle can be released for shipment, it undergoes a final series of checks in the pre-delivery quality assurance zone. This area acts as a last filter to catch any deviations that might have occurred during the assembly or post-test handling stages. Workers inspect tire pressure, verify that protective films are applied correctly to scratch-prone areas like door edges, mirrors, and bumpers, and confirm that all software systems are up to date. Vehicles fitted with GPS or SIM-based connectivity receive final activation or regional adjustments depending on local telecom regulations and data privacy laws. Another important step here is the market-specific homologation procedure. While the Octavia platform is globally standardized, various regulatory requirements differ from country to country. Vehicles destined for the UK, for example, require right-hand drive steering, headlight angle adjustment, and specific compliance markings on safety stickers and child lock labels. Similarly, North African or Middle Eastern versions often come with enhanced cooling systems, battery conditioning for high-temperature zones, and multilingual interfaces for infotainment and vehicle manuals. Each car is thus finalized for its end-user region with absolute attention to detail. Once cleared for dispatch, the logistical journey begins. Cars are loaded either onto multi-deck car carrier trucks or specialized automotive freight trains, depending on destination. For continental European markets, rail transport is the norm, as it allows for the movement of dozens of vehicles at once with low emissions and high security. These trains are purpose-built with adjustable platforms to accommodate various vehicle heights and lengths, and the loading process itself is conducted using hydraulic ramps and wheel guides to prevent any possibility of contact or scratching. Vehicles are secured in place using soft straps over the tires, never hard points on the bodywork, to avoid any damage. Drivers and loaders follow strict speed limits and turning angles during the loading process, and each movement is logged electronically with timestamps and operator ID for full traceability. The outbound transport system functions on just-in-time scheduling. Transport is aligned tightly with dealership stocking cycles and customer orders, meaning that most Octavias are delivered to retail networks within days of completion. For overseas markets such as Australia, Japan, or South Africa, the vehicles are routed to maritime logistics hubs, most notably in German ports like Bremerhaven or Hamburg. Here, cars are parked in holding zones until their shipping vessel arrives. Before boarding the ships, known as roll-on, roll-off, or ro-ro vessels, each Octavia undergoes a salt spray protective procedure, which includes the application of temporary wax coatings on vulnerable areas like undercarriages and wheel wells. Mirrors are often folded in or protected with soft plastic covers, and battery terminals may be disconnected during long journeys to preserve charge levels. Ro-ro vessels are essentially floating parking garages. Cars are driven into the lower decks via wide ramps, then secured in rows using floor hooks and wheel chocks. Temperature and humidity are monitored throughout the voyage, and any incident or deviation is logged and communicated back to Skoda's central logistics team. These teams use real-time satellite tracking and predictive ETA algorithms to coordinate arrival times, customs clearance, and inland transport schedules for each destination port. Upon arrival in the destination country, the vehicles are offloaded and temporarily stored at an importer's distribution center, known in industry terms as a vehicle processing center. These centers act as a final staging ground before cars are delivered to dealerships. Here, the Octavia undergoes another series of inspections and market preparations. Protective films are removed, final cleaning is done, and country-specific accessories like license plate frames, floor mats, or regional documentation packets are added. The vehicle's onboard software may receive updates or localizations, such as voice command packs in specific dialects or region-locked infotainment functions like radio bands or mapping data. Any vehicle requiring customization at the VPC, such as fleet vehicles with special paint schemes, decals, or upfitting, undergoes a rapid accessory installation. This is also the point where final compliance documents are printed and affixed, including emission certification, tire labeling, and VIN stickers that align with the country's Department of Transportation or equivalent authority. Once cleared, the car is loaded onto local transport carriers, usually single or double-deck trucks designed for short-haul deliveries to regional dealers. These trucks operate on a tightly managed schedule coordinated between the manufacturer, logistics provider, and the dealership's sales team. Dealerships receive advance notice of incoming units, complete with full configuration specs, production history, and electronic handover documentation. This allows showroom staff to prepare for vehicle delivery, organize customer paperwork, and schedule test drives or handovers for buyers who've pre-ordered their Octavia. Upon arrival at the dealership, the vehicle enters the final stretch of its preparation lifecycle. Dealership technicians perform what's known as the pre-delivery inspection. This process involves checking battery voltage, verifying tire pressures again, updating software to the latest firmware release, and confirming that all onboard systems are functioning correctly. The technician also syncs the vehicle's telematics systems with the customer's profile if it's a connected vehicle, ensuring seamless onboarding for the driver. Exterior cleanliness and presentation are paramount here. The vehicle is washed, dried, and polished. Any interior protection, seat covers, plastic film on displays, is removed carefully to preserve the new car sensation. The vehicle's infotainment system is often demoed for the customer in advance, showing off features like wireless Apple CarPlay or Android Auto, adaptive cruise control settings, or integrated Skoda Connect services. The car is now ready for customer delivery. But beyond just logistics, the entire system that supports the delivery of the Skoda Octavia is also an achievement in manufacturing scalability and digital synchronization. Every car, from the moment a production slot is assigned to the instant its keys are handed over to a new owner, is tracked, scheduled, configured, and quality controlled to within an inch of perfection. Even after the sale, onboard diagnostic tools and telematics systems report service needs, software, update availability, and potential issues, creating a lifecycle loop that feeds directly back to Skoda's engineering and production planning teams. For example, if a particular batch of Octavias reports slightly increased wear in rear suspension bushings under certain climate conditions, engineers can trace the data back to specific suppliers, production dates, and even sub-batch quality readings. This creates a feedback loop that not only improves future vehicles, but enhances predictive maintenance and customer satisfaction. Behind the gleaming bodywork, smooth ride, and modern technology of each Skoda Octavia lies a staggering network of systems, people, machinery, and logistical engineering. From zinc-coated steel coils and precision robotic welds to cross-continental transport vessels and digital dealership diagnostics, the Octavia isn't just built, it's orchestrated in harmony with thousands of moving parts and processes, each time to perfection. And all of it, every robot weld, every bolt tightened to exact Newton meters, every barcode scanned, is done not simply to build a car, but to deliver an experience, one of reliability, safety, performance, and pride of ownership. That's the promise that begins in the factory and ends in the driver's seat. To truly understand the scale and precision behind Skoda Octavia production, one must look beyond the factory floor and consider the intricate network of component suppliers and upstream systems that feed into the assembly line. For every car that takes shape in the factory, hundreds of specialized parts must arrive on time, in the right sequence, and in the correct specification. This vast, synchronized network is known in the automotive world as the supply chain, and in the case of Skoda, it's a marvel of real-time coordination, supplier partnerships, and just-in-time logistics. Each Skoda Octavia comprises over 6,000 individual parts. These components range from large visible systems like wheels, windshields, and headlights to invisible but critical parts like engine sensors, fuel injection regulators, gasket seals, and control module chips. Roughly 65 to 70% of these parts are manufactured by Tier 1 suppliers, companies that deliver fully assembled modules or high-value systems directly to the carmaker. The remaining proportion includes Tier 2 and Tier 3 suppliers that deliver subcomponents to the Tier 1s for further integration. Consider the dashboard module, for example. This is not simply a plastic structure. It includes integrated climate ducts, wiring harness brackets, infotainment mounts, and sometimes even embedded ambient lighting strips. A supplier like Faurecia or Lear might produce this complete dashboard unit off-site at a satellite plant located within 50 to 100 kilometers of the main Skoda facility. Their production runs in parallel with Skoda's own line, synchronized by shared production schedules and EDI systems. These EDI platforms are the backbone of modern automotive manufacturing. Through these systems, Skoda communicates real-time build orders to each supplier based on customer demand, line performance, and inventory levels. If a sudden influx of Octavia orders requires an uptick in 1.5 TSI engines with manual gearboxes, Skoda's system sends this data down the chain, prompting engine module suppliers to adjust output and delivery timing. This just-in-time model reduces storage needs and waste, but it requires near-perfect execution and reliability across the board. Every part entering the Skoda plant is tagged with unique barcodes or RFID labels. Upon arrival at the factory gates, incoming deliveries are scanned, inspected, and logged. The parts are then sent either directly to the line or stored in high-efficiency automated warehouses called ASRS. These towering computer-controlled storage units use robotic cranes and conveyors to quickly retrieve parts as needed, feeding them into the production line in a seamless, real-time flow. But the supply chain is about more than just timing. Quality control is paramount. Each supplier is required to adhere to Skoda's supplier quality standards, which are monitored through periodic audits, statistical process control data, and end-of-line checks. If a batch of components falls outside tolerance, say windshield washer motors with torque output below spec, they are quarantined and the supplier is notified immediately via automated quality feedback portals. This attention to quality also extends to the software components in modern Octavias. Today's cars are as much digital machines as they are mechanical ones. Software for ECU modules, infotainment units, ADAS, and telematics is developed months in advance and tested in closed-loop systems before being validated for installation. These software packages are pushed to the factory through secure networks and flashed onto control modules during vehicle assembly. Security is paramount here, and all software updates are cryptographically signed to prevent tampering or breaches. Now, let's turn to automation, one of the defining features of modern Skoda production. While humans remain central to the assembly process, particularly in tasks requiring judgment, dexterity, and customization, the factory itself is driven by an intricate web of automated systems. Conveyors, robots, AGVs, and digital twins all work in harmony to keep the line moving with minimal interruption. AGVs are one of the most visually striking elements of this system. These robotic delivery vehicles navigate factory floors autonomously, delivering everything from suspension arms to steering wheels to the correct workstation, guided by a combination of magnetic tracks and onboard LiDAR systems. Each AGV is linked to the MES and can reroute itself based on real-time production changes. For example, if a specific model is delayed in paint, the AGV carrying its corresponding seat set can be redirected to a holding buffer without human intervention. Overhead, conveyor systems run in tandem with the floor-level automation. These ceiling-mounted rail systems transport car bodies from one section of the plant to another, lifting and rotating them to allow ergonomic access for workers and robots. In some areas, these conveyors also include turntables and elevator modules that adjust height and orientation based on the assembly phase. This ensures not only productivity, but also worker safety and comfort. One of the most powerful tools in Skoda's production arsenal is its use of digital twin technology. Every car moving down the line has a virtual counterpart in the cloud, an exact digital representation of its configuration, assembly status, component origins, and inspection results. This digital twin is updated in real time and can be accessed by plant managers, quality engineers, and logistics coordinators. If an issue arises, say a misalignment detected in a body panel, the digital twin records the anomaly, associates it with the production station and shift in which it occurred, and notifies the relevant teams for root cause analysis. Digital twins are also critical in training and simulations. Before a new variant of the Octavia is introduced, engineers and planners can simulate the entire build process, testing new tools, layouts, or work sequences in virtual space. This allows Skoda to implement changes quickly with minimal disruption to ongoing production. It also reduces the number of physical prototypes needed for process validation, saving both time and cost. While robotics handle many of the repetitive and high-precision tasks, human workers remain essential, particularly in the trim and final zones where interiors, wiring, and complex assemblies come together. To assist them, Skoda deploys a suite of ergonomic tools and digital aids. Torque-controlled power tools connected to overhead reels allow workers to fasten components without strain. Visual instructions and torque values are displayed on smart monitors at each station, updating in real time based on the vehicle moving down the line. Smart gloves and wearable scanners are also used, allowing technicians to confirm part identity and orientation before installation. Each human operator is trained extensively, with many going through weeks of classroom instruction, simulator-based practice, and shadowing experienced colleagues. Certification is required for each workstation, and retraining is done periodically or whenever a new process is introduced. Safety is integral to all of this. Sensors monitor motion zones to prevent collisions. Alarms trigger if tools deviate from preset thresholds, and workspaces are equipped with height-adjustable platforms and cushioned mats to reduce fatigue. Behind all of this is a powerful production planning system. Long before a single Octavia reaches the line, planners model capacity forecasts, supplier lead times, labor scheduling, and shift rotation schemes using AI-based algorithms. These tools factor in order backlogs, regional model demand, holidays, and even weather patterns that might affect logistics. If a snowstorm is predicted in a key transport corridor, the system automatically recommends schedule shifts or alternate distribution routes to avoid disruption. Energy efficiency is another area where Skoda has made major strides. The factory is equipped with heat recovery systems, solar arrays on the roof, rainwater harvesting systems, and intelligent lighting that adjusts based on occupancy and daylight levels. Paint shops, traditionally among the highest energy consumers in automotive production, are now equipped with dry scrubber technology and thermal recirculation to minimize waste. Even conveyor motors are equipped with regenerative braking systems to recover energy during deceleration phases. Sustainability doesn't stop at the factory gates. Suppliers are audited not just for quality and delivery performance, but also for environmental and social responsibility. Skoda enforces compliance with ISO 14001 standards across its tiered supply network and encourages local sourcing where feasible. Packaging materials are standardized and reusable, and component shipments are consolidated wherever possible to reduce carbon footprint. To further appreciate the engineering and manufacturing depth of the Skoda Octavia, one must explore the extensive customization capabilities and flexible production architecture that allows this single vehicle line to cater to a wide global audience. The Octavia is not a one-size-fits-all car. It is offered in multiple body styles, powertrain options, interior trims, and equipment levels, all of which are supported by a sophisticated manufacturing system built upon modularity, scalability, and lean manufacturing principles. At the heart of Skoda's flexibility lies the Volkswagen Group's modular Querbaukasten, or MQB platform. Introduced to harmonize development across different vehicle classes, MQB is a transverse modular toolkit that allows shared use of components such as engines, transmissions, suspension geometry, and electrical architectures across various models. In the case of the Octavia, it shares its underlying platform with vehicles like the Volkswagen Golf, Seat Leon, and Audi A3. This commonality enables Skoda to produce multiple variants of the Octavia: sedan, wagon, hybrid, gas-powered, diesel, and even mild hybrid versions, without requiring completely separate production lines. Rather than viewing the Octavia as a single product, Skoda treats it as a configurable structure within a tightly coordinated production matrix. When a customer places an order, either through a dealership or an online configurator, that order flows into Skoda's central planning database, where it's translated into a digital build sheet. This document specifies every aspect of the vehicle: engine type, transmission, drive layout, infotainment system, upholstery, wheel design, active safety packages, regional adaptations, emission certifications, and even factory-installed accessories like roof bars or tow hitches. Each of these variables is governed by a set of compatibility rules managed by Skoda's product configuration logic. For example, a high-output diesel engine may not be available with the base trim level due to cooling and chassis constraints. Similarly, specific radar-based safety systems might only be installable on variants with a certain type of front bumper or interior digital cockpit. These conditional dependencies are resolved automatically by the back-end systems, which check for engineering feasibility before locking in the order. Once an order is confirmed, it is slotted into a dynamic production schedule that balances model mix, resource availability, and factory efficiency. Importantly, Skoda does not build vehicles in strict order of sales. Rather, it builds them in an optimized sequence that minimizes setup time, balances labor load, and stabilizes part consumption rates. This method, sometimes referred to as level scheduling, is one of the cornerstones of lean manufacturing. It prevents bottlenecks, allows for better supplier coordination, and reduces the amount of time the car spends in the factory. As a result, two cars traveling down the line might look identical from the outside, but be completely different beneath the surface. One a plug-in hybrid with heated rear seats and check navigation, the other a base model petrol version for export to North Africa. To manage this complexity, each station along the line reads the vehicle's digital build sheet in real time. Screens above the workstations display step-by-step instructions tailored to that exact configuration, while pick-by-light systems guide workers to the correct bins and component trays. This is particularly important during interior assembly, where the number of possible permutations is vast. From dashboard colors and decorative inserts to seat foam densities and steering wheel types, the interior is one of the most customized parts of the car. Workers receive seating units pre-tagged with RFID matched to the car via an automated delivery system. The steering column, infotainment interface, gear selector, and even pedal assemblies are chosen based on each vehicle's order code. Robotic torque arms are reprogrammed automatically to apply different fastening sequences depending on the equipment level and trim variant. The same modular logic applies to the powertrain station. The MQB platform allows various engine and transmission combinations to be mounted onto the same chassis architecture. Whether a car is receiving a 1.0 TSI petrol engine or a 2.0 TDI diesel with all-wheel drive and DSG transmission, the mounting points, wiring harness routing, and cooling integration follow standardized paths. The robotic systems that perform engine marriage operations adjust in real time based on the digital instruction set received for each car. Emissions compliance is another area where the system's flexibility shines. Vehicles bound for different regions must meet different regulatory standards: Euro 6D in Europe, Bharat, Stage 6 in India, or Tier 3 in the United States. This affects more than just engine calibration. It can influence the selection of catalytic converters, onboard diagnostics, fuel vapor recovery systems, and exhaust layout. The assembly line is capable of dynamically adapting these configurations during the final powertrain integration phase. Emission sensors are tested and validated before the car moves to final quality check, ensuring full compliance before leaving the plant. This high degree of customization has forced Skoda to develop exceptionally refined in-house logistics and traceability tools. Every part, from a bolt in the seat frame to the circuit board inside a camera module, is traceable back to its source, down to the supplier batch and timestamp. If a defect is later discovered in a specific part, such as a faulty capacitor in an ABS module, Skoda's quality team can instantly identify all affected vehicles, notify dealers, and even pre-position replacement parts for proactive service campaigns. But the complexity doesn't end at physical hardware. Modern Octavias are packed with software-controlled systems: lane assist, adaptive cruise control, parking sensors, matrix LED lighting, automatic emergency braking, and connected infotainment platforms. Each of these systems has embedded firmware that must be updated and calibrated before delivery. In some cases, over-the-air updates can be performed after the car is sold, but many functions still require factory-level activation and testing. To streamline this, Skoda uses central configuration tools that compile a software bill of materials for each vehicle. As the car moves through assembly, each electronic control unit is flashed with its specific firmware version, encrypted and authenticated via secure keys. A final system integration test validates that all ECUs are communicating properly, known as a KN bus verification, and that diagnostics are error-free. If any faults are detected, the car is automatically diverted to a diagnostics bay for further analysis. Such granularity and flexibility would not be possible without an empowered and highly skilled workforce. Skoda invests heavily in training and upskilling its production teams. Every new employee undergoes a rigorous onboarding program that includes mechanical skills, safety procedures, quality assurance basics, and an introduction to the Skoda production system. For specialized roles like engine mounting, suspension calibration, or electrical integration, additional certifications are required. These are renewed annually to ensure procedural consistency and up-to-date knowledge. Continuous improvement, or Kaizen, is another foundational principle. Employees are encouraged to identify inefficiencies or risks and propose improvements through structured feedback channels. Many line-side innovations, such as tool redesigns, ergonomic adjustments, or improved material handling flows, originate from shop floor operators. Each suggestion is reviewed by a dedicated process engineering team and, if feasible, rapidly prototyped and implemented. Even the work environment itself is engineered for performance and health. Skoda's factories are designed with natural light corridors, clean air circulation systems, sound dampening materials, and climate-controlled zones. Workstations are height adjustable, parts bins are positioned within optimal reach distances, and ambient noise levels are monitored to prevent long-term exposure risks. In areas with repetitive motion, exoskeletons or assistive lifting arms are provided to reduce physical strain. Skoda's ability to build thousands of highly individualized vehicles per week is not simply a triumph of machinery. It's a reflection of disciplined process design, human system integration, and scalable modularity. Whether assembling a performance-oriented Octavia RS with sport suspension and dual exhaust, or a fuel-sipping mild hybrid for city commuting, the line adapts fluidly. Every Octavia is not just a copy of the last. It is a response to a unique customer need, tailored precisely and efficiently thanks to the architecture of customization that Skoda has refined over decades. Inside the sleek, meticulously organized production halls, where Lexus vehicles are brought to life, craftsmanship meets cutting-edge automation in one of the most refined automotive manufacturing processes in the world. The journey of a Lexus begins not on the factory floor, but in the minds of engineers, designers, and master craftsmen known as Takumi. These artisans, with decades of experience, help shape the philosophy of quality and precision that defines every Lexus model. Before any physical materials are touched, the vehicle undergoes countless hours of design and digital simulation. Designers model each contour and surface using advanced CAD software, ensuring aerodynamics, aesthetics, and structural integrity are in harmony. Simultaneously, engineers plan out the vehicle's underlying architecture, the chassis, drivetrain, suspension system, and electronic infrastructure, all of which must integrate seamlessly in the final product. Once virtual models and prototypes are validated through digital stress testing and aerodynamic simulation, the blueprint is ready for translation into physical production. Raw materials for Lexus vehicles are sourced globally but meet stringent internal quality requirements. The main material used in the body is high tensile steel, although aluminum and lightweight composites are becoming increasingly common, especially in performance or hybrid models. Steel coils arrive at the plant in massive rolls and are carefully inspected for surface defects, strength, and elasticity. These coils are then unrolled and fed into precision cutting machines. Automated laser cutters slice the sheets into individual panels, doors, roofs, hoods, and side walls, each shaped with millimeter accuracy. These panels then undergo a series of progressive stamping operations. Gigantic hydraulic presses weighing several hundred tons pound each steel sheet into its designated shape using specialized dies. These dies are meticulously engineered and periodically recalibrated to maintain tolerances as tight as a fraction of a millimeter. During stamping, features like creases, curves, and reinforcement ribs are embedded directly into the metal, contributing both to design and structural integrity. The next stage is body-in-white assembly, where the vehicle's skeletal structure begins to take shape. Robotic arms equipped with weld guns perform thousands of spot welds per car, joining the stamped panels together into a rigid, seamless shell. Lexus factories often employ laser welding for specific areas like roof joints or pillars, achieving a cleaner finish and stronger bonds than traditional methods. A select group of highly trained technicians also perform manual welding in hard-to-reach areas, ensuring consistency across every build. Cameras and sensors continuously monitor the alignment of every panel to detect even the smallest deviations in fit or finish. With the raw body now assembled, it enters the paint shop, a controlled environment with extremely high cleanliness standards. Prior to painting, the body is submerged in an electrodeposition tank, where it's coated with a rust-inhibiting primer using an electric charge to bind the molecules to the steel. This anti-corrosion step is essential for longevity. After that, the car body passes through an automated sanding and cleaning line to prepare the surface for color application. Paint is applied in multiple coats: primer, base coat, and clear coat, using robot sprayers that mimic human wrist movements for a natural, even finish. Each paint layer is flash dried in curing ovens set to precise temperatures, and between each layer, the body is inspected under UV and white light to catch any inconsistencies or inclusions. Lexus offers a range of colors, but each hue is carefully developed to interact with lighting and body shape in a specific way. The final clear coat is cured in a high-temperature bake oven, after which the body is cooled slowly to prevent microcracking or warping. As the painted shell makes its way to general assembly, the mechanical heart of the Lexus is being prepared in parallel. Engine blocks, transmissions, hybrid drive units, and other powertrain components are either produced in-house or arrive from specialized manufacturing partners. These components undergo their own precision machining processes. Crankshafts are ground to micron-level smoothness. Cylinder heads are pressure tested for leaks, and valve trains are assembled under cleanroom conditions to prevent particulate contamination. Every engine is hot tested with synthetic oil and run on a bench to simulate driving conditions, ensuring it meets Lexus's strict vibration, noise, and torque standards. In the chassis line, the painted body is now mounted onto its corresponding suspension and drivetrain system. This is performed on synchronized conveyor lines where the body and the chassis meet in a process called marriage. Sophisticated vision systems and robotic arms align the two structures with such precision that no manual corrections are necessary. Once married, the vehicle receives its fuel system, braking components, and exhaust system, each installed by a combination of robots and skilled technicians. Wiring harnesses, which can include several kilometers of cable, are laid out using templates and fixed in place by specialized machines. These harnesses connect the vehicle's electronic control units, sensors, infotainment systems, and safety devices. Interior assembly follows, beginning with the installation of insulation, sound deadening mats, and undercarpet padding. Lexus places a high priority on NVH, noise, vibration, and harshness. So every panel is fitted with dampening materials to ensure a quiet ride. Seats are assembled in a separate clean area and installed using automated arms with torque sensors that ensure fasteners are neither under nor over tightened. Dashboard modules, which include HVAC controls, infotainment screens, and digital displays, are pre-assembled on sidelines and inserted into the cabin in one synchronized motion. The steering column is calibrated for tilt and telescopic movement and connected to electronic steering systems, while airbags and sensors are fitted with strict adherence to safety protocols. Once the interior and exterior trim are installed, including lighting assemblies, mirrors, grills, and body moldings, the vehicle proceeds to the fluid fill area. Here, robotic nozzles inject the precise quantities of engine oil, brake fluid, coolant, transmission fluid, and refrigerant for the air conditioning system. Each fill is tracked by weight and volume sensors to guarantee consistency. After this, the car undergoes wheel mounting and torque checking using specialized tools that record every bolt's torque signature to ensure they meet Lexus's specifications. Now fully assembled, the car enters the dynamic test stage. Every Lexus is driven on a test track or rolling road that simulates real-world driving conditions. During this phase, technicians listen for abnormal noises, feel for vibrations, and monitor electronic systems to confirm everything operates within design parameters. Brake response, suspension feel, steering feedback, and drivetrain behavior are all evaluated in real time. Vehicles equipped with advanced driver assist systems undergo calibration and functional checks using target boards and optical sensors. If any anomaly is detected, the car is flagged and routed to a correction station for adjustments or part replacement. Quality assurance is not a single checkpoint, but a continuous presence throughout the assembly process. Hundreds of sensors, scanners, and cameras monitor every assembly station. Torque tools are networked into the plant's central server to ensure bolts are always fastened correctly. Paint is checked not only by human inspectors, but also by multi-angle robotic sensors that detect flaws invisible to the human eye. Final inspection is carried out by Takumi masters, who evaluate the vehicle's tactile and visual quality. They look at panel gaps, feel the texture of materials, and assess the overall aesthetic with a level of scrutiny that only comes with decades of experience. Once cleared for shipping, the car is fitted with temporary protective coverings on high-contact surfaces like the hood, mirrors, and interior trim. It then moves to the logistics center where it's sorted by destination. Lexus uses a just-in-time distribution system to minimize storage time and ensure each vehicle arrives at the dealership in showroom condition. Transport is typically handled via rail or enclosed trucks, depending on the destination. Some markets require additional port processing, such as compliance with regional emission standards or language-specific infotainment updates before the vehicles are delivered to showrooms. What truly sets Lexus apart, however, is not just its meticulous production, but the ethos that underpins it. The Lexus production system, derived from the famed Toyota production system, emphasizes continuous improvement, waste reduction, and human-centered manufacturing. Workers at every level are encouraged to stop the line if they notice an abnormality, a culture known as jidoka or built-in quality. Every process is subject to kaizen or incremental improvement, meaning the manufacturing floor is in a constant state of optimization. Even the robots are not fixed assets. Their programming is continuously updated based on feedback from human workers. This seamless blend of human mastery and robotic precision results in a vehicle that embodies both technological advancement and handcrafted excellence. From the silent glide of the paint robots to the calm concentration of a Takumi applying finishing touches to a wooden inlay, each Lexus carries within it the philosophy of omotenashi, a spirit of hospitality and attention to detail that transcends machinery. In a world increasingly dominated by automation, the Lexus factory is a compelling reminder that the future of manufacturing lies not in replacing the human touch, but in elevating it. Inside the rugged and powerful world of Jeep manufacturing, toughness isn't just a design principle. It's embedded in every step of the industrial process. Jeep vehicles, renowned for their off-road capabilities and iconic status, are built in factories that combine high-strength materials, advanced robotics, and decades of engineering experience to produce vehicles capable of handling everything from city streets to extreme terrain. The story of how a Jeep comes to life inside a factory is a narrative of precision, durability, and relentless testing, all shaped by a legacy that dates back to World War II. It all began in the early 1940s, when the US military needed a lightweight, go-anywhere reconnaissance vehicle. What followed was the birth of the Willys MB, the direct predecessor to the Jeep. Over the decades, the brand evolved from a military utility vehicle to a global symbol of adventure, strength, and freedom. Today, Jeep models like the Wrangler, Grand Cherokee, and Gladiator are produced in high-tech manufacturing facilities that carry forward the DNA of the original while incorporating the very latest in automotive production technology. The process begins long before the first bolt is tightened. It starts with engineering teams who define the specifications of each new model based on performance expectations, off-road capability requirements, safety standards, and customer feedback. Computer-aided design and simulation tools help model every component, from the ladder frame chassis of a Wrangler to the unibody structure of a Grand Cherokee, ensuring each part is strong, lightweight, and optimized for performance. Crash simulations, airflow analysis, and even water fording simulations are run digitally, months before any physical part is made. Once the vehicle design is finalized, raw material procurement begins. Jeep factories rely heavily on high-strength steel alloys, aluminum, and composite plastics. These materials arrive at the plant as massive coils or billets and are rigorously inspected for imperfections. Each batch is traceable, meaning any material used in a Jeep can be tracked back to its origin. This ensures consistency, compliance with safety regulations, and accountability. These raw materials first enter the stamping plant, where they are transformed into body panels and frame components. Enormous stamping presses, some standing 3 stories tall, shape the steel using dies that apply thousands of tons of pressure. Each panel must conform to strict tolerances, as even a 1mm misalignment could throw off the entire vehicle structure. Jeep vehicles, especially models designed for off-road use, require thicker and more robust structural reinforcements than many consumer vehicles. This means extra ribbing is built into the dies, and additional pass-throughs in the press lines ensure structural rigidity in critical load-bearing areas like wheel arches and suspension mounts. The formed body panels are then routed to the body shop, where robotic welding arms assemble them into the vehicle's skeleton. For a Jeep Wrangler, this means bringing together the floor pan, sidewalls, roof structure, and rear panels into a boxy, trail-ready frame. The welds must be strong and consistent, especially for a vehicle expected to endure torsional flex and harsh impacts off-road. Jeep factories use a mix of MIG welding, laser welding, and resistant spot welding. Over 5,000 welds go into each body, with robots performing the majority, while human technicians focus on quality critical joints or hard-to-reach spots. A unique aspect of Jeep production, especially for the Wrangler, is the modularity of the body. Doors, roofs, and windshields are designed to be removable, which adds complexity during assembly. Tolerances must be tighter because customers expect parts to detach and reattach easily, without leaks or vibrations. This means extensive calibration and fit testing is built into the body shop workflow. Every door frame and roof panel is test fitted and adjusted using pneumatic tools and laser measuring systems to ensure flawless alignment. Once the skeletal body is complete, it heads to the paint shop, one of the most technologically advanced areas in the plant. The vehicle first undergoes a thorough cleaning and surface preparation. This includes a dip in a phosphate bath to clean off oils and contaminants, followed by electrocoating, where the vehicle is submerged in a tank and an electrical current bonds an anti-corrosion primer to every surface, including hidden cavities. After drying, the vehicle enters the painting booths. Here, robots apply multiple coats of paint, primer, color, and clear in a dust-free environment. Jeep offers bold colors inspired by nature and adventure, such as Sarge Green or Firecracker Red, each mixed with precise pigment ratios and applied with fluidic nozzles that mimic human spray techniques. Each coat is oven-cured to form a resilient finish, capable of withstanding UV exposure, mud, salt, and rocks kicked up from the trail. After painting, the body shell enters the general assembly area, the heart of the production line. This is where the Jeep transforms from a metal shell into a fully equipped vehicle. It begins with insulation, sound-deadening materials, and sealants applied inside the cabin. For Jeep models, this includes water-resistant treatments, as many vehicles are designed for water fording. Door seals and body gaskets must meet strict compression and durability standards. Wiring harnesses are installed next, and these are more complex than ever. Modern Jeeps feature hundreds of sensors, infotainment systems, off-road driving modes, and safety technology. These harnesses are laid in place using programmable placement arms and secured with clips, zip ties, and heat shrink tubing, depending on the location and exposure to moisture or vibration. Next comes the marriage of the chassis and powertrain with the painted body. For body-on-frame vehicles like the Wrangler and Gladiator, the heavy-duty steel frame is assembled separately, including solid axles, coil or leaf springs, differentials, skid plates, and suspension arms. The frame is then bolted to the body using hydraulic lifts and torque tools that ensure each fastener meets exact tension values. For unibody models like the Cherokee or Compass, this integration happens earlier in the line with subframes bolted directly to the structure. Jeep powertrains are built for torque, durability, and versatility. Engines such as the Pentastar 5.6, the Hurricane turbocharged inline 4, or diesel options are assembled in parallel engine plants where they undergo machining, balancing, and dyno testing. Each engine is hot tested for leaks, performance, and emissions compliance. Transmissions, white, whether manual, automatic, or dual clutch, are mated to the engine on a subline, forming the complete drivetrain assembly. This unit is then raised into the chassis using synchronized lifts and installed with precision fasteners that ensure alignment and vibration isolation. Drivetrain components are connected next. Drive shafts, transfer cases, and locking differentials, all essential for Jeep's off-road performance, are installed and calibrated. Specialized torque sensors verify that each fastener is within spec, and camera systems double-check routing and connections. Jeep's 4x4 systems require precise calibration, especially when electronic terrain management systems are used. These allow the driver to switch between mud, sand, snow, and rock crawling modes, adjusting throttle mapping, gear ratios, and traction control accordingly. Now, the vehicle moves into interior and exterior trim assembly. Seats, dashboards, consoles, and trim panels are installed by teams working in pods, with each station responsible for fit, function, and finish. For premium models like the Grand Cherokee Summit, this includes hand-stitched leather, real wood accents, and digital clusters that must be pixel perfect. Each infotainment screen is tested for dead pixels and software integrity before leaving the station. Rugged models like the Wrangler Rubicon get special features such as washable floor mats, reinforced roll bars, and waterproof switches. Exterior components like grills, bumpers, lighting assemblies, and badging are added in tandem, with a final alignment check to ensure symmetry and fit. Next, the vehicle proceeds to the fluid fill station, where all vital systems are charged with fluids: motor oil, transmission fluid, differential gear oil, coolant, brake fluid, power steering fluid, and refrigerant. Each fluid fill is done robotically, with flow meters and digital monitoring to verify quantities and eliminate the risk of leaks. Finally, the Jeep enters a rigorous quality and testing phase. This begins with a rolling road test, where the vehicle is driven on dynamometers to test drivetrain performance, braking, steering, and electronic controls. Special off-road simulations are run to verify that lockers engage, hill descent controls activate, and all-wheel drive functions correctly. Vehicles are then driven over test tracks with potholes, speed bumps, and articulation ramps to simulate real-world terrain. Water intrusion tests involve spraying the vehicle at high pressure from multiple angles to ensure seals hold. Each Jeep undergoes a final inspection by trained quality specialists who look at paint finish, interior trim, panel gaps, and feel for any mechanical irregularities. Light tunnels and tactile checks help identify imperfections. Every vehicle is barcoded and logged, with full traceability of every component. and test result. Once approved, the vehicles are sent to the logistics center. Some are loaded onto railcars for cross-country shipment, while others are driven onto enclosed trucks for dealer delivery. Jeeps destined for export are often protected with shrink wrap, and some may be reconfigured with market-specific hardware or software updates before final delivery. Inside the meticulously engineered world of Corvette production, speed, performance, and precision craftsmanship converge inside one of the most specialized automotive manufacturing facilities in the world, the General Motors Bowling Green Assembly Plant in Kentucky. This is the only place on Earth where every Corvette is built, from the very first weld to the final roar of the engine. From hand-built V8 power plants to aerospace-grade composite panels, the modern Corvette is the result of decades of performance heritage married to cutting-edge manufacturing science. The process of building one of America's most iconic sports cars isn't just an industrial operation. It's an orchestrated symphony of engineering, robotics, skilled labor, and quality control, working together to create a machine that is capable of competing with the best exotic vehicles on the planet. The Corvette's legacy stretches back to 1953, when the very first model rolled off a makeshift production line in Flint, Michigan. It was a lightweight, fiberglass-bodied roadster powered by a modest inline-six engine, but that humble beginning sparked a revolution. Over the decades, the Corvette evolved, gaining V8 engines, refined suspensions, racing pedigree, and global prestige. In 2020, the Corvette took its biggest leap yet. The C8 generation transitioned to a mid-engine layout, fundamentally altering how the car is designed, built, and performs. This change not only shifted the car's balance and handling characteristics, but required a complete rethinking of the manufacturing process. The factory itself was overhauled to accommodate the new architecture, including the installation of hundreds of millions of dollars worth of robotics and tooling, all to support the Corvette's transformation into a true supercar. The process begins with the core of the vehicle, the chassis and structural frame. The C8 Corvette uses a bespoke aluminum space frame that provides high torsional rigidity with relatively low weight. The aluminum arrives at the factory in billet or coil form, sourced from certified suppliers meeting strict metallurgical standards. Before fabrication, each aluminum piece is scanned for flaws using non-destructive testing methods, such as ultrasonic or X-ray analysis. Once cleared, the aluminum is extruded, stamped, or hydroformed into the necessary components, including rocker beams, cross members, and crash structures. The hydroforming process is particularly fascinating. In this technique, aluminum tubes are placed into dies and then expanded into their final shape using pressurized hydraulic fluid. This allows for complex, hollow parts with superior strength-to-weight ratios, ideal for the Corvette's safety and performance needs. After forming, robotic systems with high-precision weld arms begin assembling the frame using a combination of MIG welding, laser welding, and structural adhesives. The fully assembled frame is placed on a rotating jig that allows for 360-degree access, ensuring welds are placed with micron-level precision. Each frame is scanned with a 3D vision system to verify all dimensions before moving to the next station. While the frame is coming together, another crucial part of the Corvette, the body panels, is being fabricated. Unlike most mass-market vehicles, the Corvette's skin is made from lightweight composites, including fiberglass reinforced plastics, carbon fiber, and sheet-molded compounds. These materials provide strength and shape without adding the bulk of traditional steel panels. Fiberglass panels are formed through a process called compression molding, where pre-cut fiberglass mats are placed in heated molds and compressed under extreme pressure with resin. Carbon fiber parts, such as the front splitter or roof panels in high-performance trims, are layered by hand or through automated layup machines, then cured in industrial autoclaves that apply heat and vacuum pressure to harden the epoxy resin binding the fibers. Each panel is hand inspected for voids, fiber alignment, and surface imperfections before heading to paint. Since composites expand and contract differently than metal, Corvette panels require their own specialized painting process. The painted body panels must not only match each other perfectly, but must maintain color integrity over time, even under high UV exposure and heat. Paint robots apply multiple coats: primer, base, metallic or pearl layer, and clear coat, with each step oven cured. Color matching is so critical that Corvette offers customers a paint inspection under natural light to approve their vehicle's finish before delivery. Back at the main assembly line, the aluminum chassis and painted body panels are now ready to come together. The chassis first moves through the marriage process, where it is combined with the suspension, brakes, steering components, and cooling systems. Each suspension arm is installed using robotic torque tools that log every bolt's torque value in a centralized quality database. Corvette's advanced suspension options, including magnetic ride control and adjustable dampers, are calibrated at this stage using diagnostic computers connected to the vehicle's internal CAN bus system. The next major milestone is the installation of the powertrain. Unlike most vehicles, Corvette engines are not installed en masse by an overhead crane or conveyor. Instead, each engine is mounted into a subframe along with the dual clutch transaxle and rear differential. Then the entire unit is raised into the car from below using an automated lift platform. This method, called a cradle install, allows for better alignment and reduces stress on the vehicle's structure. The C8 Corvette uses a rear mid-engine layout, so the mounting process is complex and requires exact alignment of multiple mounts, fluid lines, wiring harnesses, and cooling ducts. The engine itself is built at the Performance Build Center, a special clean room inside the Bowling Green factory where trained technicians hand assemble each V8 by hand. In fact, Corvette customers can even pay to participate in this process through the Engine Build Experience program. Every engine is constructed using torque-to-yield fasteners, precision-balanced rotating assemblies, and individually tested components. Pistons are matched by weight within grams. Valve lash is measured and adjusted to strict tolerances. Each finished LT2 or LT6 engine is then tested using a hot run bench that simulates real-world driving conditions. Oil pressure, combustion noise, RPM range, and emissions are all logged before the engine is certified for installation. Once the powertrain is integrated, the Corvette proceeds to the electrical and interior assembly areas. Wiring harnesses are installed first, snaked through the monocoque chassis and connected to control modules. The vehicle's electronic brain includes over 24 modules, managing everything from traction control to wireless connectivity. Technicians perform continuity and resistance tests at every connection point. After electrical setup, the interior components are added, including carbon fiber dash inserts, premium leather seats, and customizable infotainment systems. Materials for the cabin are cut and sewn on-site with real aluminum, suede, and leather used extensively. Each interior is installed by a specialized team that ensures tight fit and finish across every seam, panel, and switch. As the Corvette approaches final assembly, exterior panels are now fitted to the car. Because composite panels are more flexible than metal, special alignment jigs are used to ensure consistent panel gaps and flush mounts. Each door, hood, and hatch is tested for smooth operation. At this stage, every Corvette begins to resemble its final form, with aggressive aerodynamic lines, wide fenders, and the unmistakable mid-engine proportions that define the C8 platform. With the vehicle now complete, it moves into the final inspection and validation zone. Here, a full suite of dynamic tests is run. The Corvette is placed on a 4-post shaker rig to simulate road vibrations and detect any abnormal noises. It is then moved onto a rolling dynamometer where the vehicle is driven up to highway speeds, while engineers test shifting behavior, throttle response, cooling system efficiency, and stability controls. Brake systems are tested for fade resistance and ABS performance. High-speed fans simulate airflow to confirm cooling under load. After dynamic testing, each Corvette is subjected to a water test. High-pressure jets are sprayed from all angles to confirm weather seals and water resistance. A separate light tunnel is used for a full-body visual inspection under high-lux lighting that reveals imperfections in paint, fit, or finish. Each vehicle is signed off by a final inspector who performs a checklist of over 100 items, ranging from alignment and cosmetic perfection to software version checks and VIN registration. If everything passes, the car is moved to the shipping prep area. Protective wrapping is applied to sensitive areas like the nose, mirrors, and roof. Final fluids are topped off, the battery is charged, and tire pressures are adjusted. Corvettes destined for US dealers are loaded onto enclosed trailers, while international units are prepared for shipping in climate-controlled containers. The factory offers a museum delivery program, allowing customers to pick up their vehicle in person at the National Corvette Museum across the street. An experience that includes a factory tour and photo documentation of their car's birth. From molten aluminum to a roaring mid-engine sports car, every Corvette that rolls off the line is a symbol of American engineering at its most passionate and refined. The attention to detail, the fusion of handmade assembly with robotic precision, and the obsessive quality control processes all contribute to a vehicle that isn't just built, it's crafted. For over 70 years, the Corvette has stood as an icon of speed and innovation, and inside the Bowling Green factory, that legacy is forged daily in metal, carbon fiber, and thunder. The journey starts as a concept, long before steel meets the press or engines meet the chassis. Engineers and designers spend months, sometimes years, refining the blueprint of a model. Every curve of the bodywork, every mechanical component, and every safety feature is planned with meticulous care. It is not simply about designing something that looks appealing, but ensuring that every component can be manufactured reliably, assembled efficiently, and maintained for years of use. When the design is finalized, the preparation for production shifts into the realm of manufacturing engineering. This is where the physical requirements for building the car are translated into a sequence of processes, machines, and assembly operations. The factory layout is adjusted to accommodate new tooling and equipment. The stamping presses, welding robots, painting lines, and assembly stations are prepared in harmony, ensuring that the entire flow of production can move like a well-orchestrated symphony. Each department communicates with the others to align their timing, capacity, and technical requirements, because any mismatch between stages can create bottlenecks that slow the entire plant. Before we even see the first car body taking shape, we must understand the raw materials that feed this system. The backbone of every Suzuki vehicle is steel, but not just any steel. High-strength automotive steel sheets arrive from steel mills in giant coils, sometimes weighing over 20 tons each. These coils are delivered by rail or truck to the factory's stamping plant. Alongside steel, aluminum panels, plastics, resins, and a variety of other materials are delivered in a steady flow. The supply chain for a car factory is an ongoing pulse of incoming goods, timed precisely so that inventory storage is minimized. Many parts and sub-assemblies come from a network of suppliers that specialize in producing components such as seats, dashboards, headlights, and braking systems. Some of these suppliers operate right next door to the Suzuki plant in what is known as a supplier park to enable just-in-time delivery directly to the assembly line. The steel coils, once unloaded, are stored for only a short period before being moved to the stamping department. This is the first truly transformative stage of car manufacturing. In a cavernous hall filled with the rhythmic thunder of stamping presses, the steel sheets are uncoiled, flattened, and fed into enormous press machines. These presses exert thousands of tons of force, shaping the steel into the contours of fenders, doors, hoods, and roof panels. Each press operation uses dies, massive, precisely machined blocks of steel that mold the sheet metal into exact shapes. The dies can weigh several tons and are swapped out when changing to a different panel design. A single car body panel often requires several stages of pressing, beginning with a rough form in the first die, followed by progressively more refined shapes in subsequent dies until the panel meets its exact specifications. During stamping, every millimeter matters. Automated optical inspection systems check the freshly pressed panels for surface defects, ripples, or dimensional deviations. Any panel that does not meet standards is set aside for recycling, its metal returned to the melting process to be reformed into new sheets. This reduces waste and ensures that only flawless panels proceed to the next stage. The next stop for these panels is the body shop, an enormous section of the plant where the raw pressed steel pieces come together to form the recognizable skeleton of a Suzuki car. Here, the air is filled with the bright sparks of robotic welding arms. The panels are loaded into large jigs and fixtures that hold them in precise alignment while robots perform spot welds. These welds fuse the panels together permanently, ensuring structural rigidity and safety. For a modern Suzuki, this stage is heavily automated, with banks of robots working in perfect synchrony. However, skilled human operators remain essential for overseeing the process, making adjustments, and performing welds in tight or complex areas where robots cannot easily reach. The construction of the car body, known as the body in white, follows a carefully choreographed sequence. The floor pan, which forms the base of the vehicle, is placed first. Side panels and door frames are aligned and welded onto it, followed by the roof, front, and rear sections. Cross members, reinforcements, and brackets are added in specific places to enhance crash protection and structural strength. Door openings are checked against strict dimensional tolerances to ensure that later, when doors are hung and adjusted, they will fit perfectly without rattling or misalignment. At various points in this body shop process, quality control engineers measure critical points on the structure using laser scanners and coordinate measuring machines. This prevents small errors from compounding into serious alignment issues later. The body in white, once fully welded, is a bare shell of gleaming steel. It has no paint, no trim, no glass, but its proportions and integrity are set for the rest of its life. Before painting, the bare metal body must be prepared meticulously. Even tiny traces of oil from stamping or dust from welding can cause paint defects. Therefore, the bodies are sent through a cleaning and pre-treatment line. They are dipped in a series of chemical baths that remove contaminants, apply a phosphate coating to improve corrosion resistance, and prepare the surface for paint adhesion. This pre-treatment line is fully enclosed, and the bodies are moved on an overhead conveyor through each tank, sometimes fully submerged to ensure every crevice is treated. The final step in this stage is a drying oven that removes all moisture. Only then does the car proceed to the paint shop, a section of the factory that feels completely different from the noisy stamping or welding halls. Here, the environment is controlled for temperature, humidity, and cleanliness. Dust particles are the enemy of smooth automotive finishes, so the entire paint area operates with filtered air and positive pressure to keep contaminants out. The first layer to be applied is the electrophoretic primer, also called E-coat. The car body is immersed in a bath where an electric current causes primer particles to bond evenly to every surface, inside and out, including hard-to-reach cavities. Once the primer is cured in an oven, sanding robots and human operators smooth the surface before the application of the base coat, which provides the car's color. Depending on the model, Suzuki may use robotic spray arms that follow precise patterns to ensure even coverage, especially around edges and curves. After the base coat, a clear coat is applied to provide gloss and protect the color from ultraviolet damage and environmental wear. Each coat is baked at controlled temperatures to ensure hardness and adhesion. As the painted shells emerge from the curing ovens, they are inspected under powerful lighting in what is often called the light tunnel. This is a controlled environment where every curve of the car's surface is scrutinized by trained eyes and optical sensors for even the smallest imperfection. A speck of dust caught under clear coat, a ripple in the finish, or an uneven tone in the paint can be enough for a vehicle to be sent back for refinishing. In automotive manufacturing, these cosmetic checks are not mere vanity. They are essential to meeting customer expectations and protecting the long-term integrity of the finish. Only after passing these surface quality tests does the body proceed to what is known as the trim line. The trim line is the first phase where the car begins to be filled with the parts that make it functional and comfortable for passengers. The process is meticulously sequenced. Every car moving down the line has a build specification loaded into the plant's production system. This ensures that the correct color interior, optional features, wiring configurations, and mechanical components are installed at exactly the right point. Workers and automated equipment access the build information via monitors or handheld devices, so there is no guesswork about which parts to install. The first installations are typically sound deadening materials. Large sheets of insulating mat are fitted to the floor, inside the doors, and sometimes behind interior panels to reduce road and engine noise. Wiring harnesses are then routed through the body. These harnesses are pre-assembled bundles of wires that carry electrical signals to lights, sensors, power windows, and entertainment systems. Fitting them correctly is critical. Any pinched wire or poor connection can lead to costly troubleshooting later. Harnesses are secured with clips and ties to prevent movement or abrasion over years of use. While the wiring is being routed, HVAC ductwork is fitted, ensuring that heating and cooling air can reach every vent in the cabin. This is followed by the dashboard assembly, which is often delivered as a complete unit from a supplier. Installing a dashboard is a delicate maneuver, as it must align perfectly with mounting points while accommodating wiring connectors, instrument clusters, and control modules. A team of technicians guides it into place and secures it with fasteners that have specific torque requirements to avoid rattles or stress on the materials. Seats are another major interior installation. These arrive pre-assembled, complete with upholstery, cushioning, and any built-in electronics such as seat heaters or airbag modules. Using mechanical assists to avoid strain, workers position the seats in the cabin and bolt them to the floor mounts. Seat positioning is not only about comfort. It has to align with seatbelt anchor points and airbag deployment geometry for safety. Parallel to interior fitting, work begins on marrying the body to the mechanical heart of the car, the chassis, and drivetrain. This is a carefully timed coordination between two moving lines, one carrying the prepared body shells and another carrying the assembled underbody module, which includes the engine, transmission, suspension, exhaust system, and braking components. The underbody is prepared in a separate section of the plant, often referred to as the chassis line, where technicians and robots assemble the engine and transmission onto a subframe, attach the front and rear suspension assemblies, mount the exhaust system, and connect steering linkages. In the case of Suzuki's smaller passenger vehicles, these assemblies are designed to be compact yet easy to service, with many components integrated into modular subframes. This not only speeds up initial assembly, but also allows for easier maintenance during the vehicle's lifetime. The wheels and tires are sometimes fitted at this stage. though final torque on wheel nuts may be left until later in the process to account for transport considerations within the factory. The moment known as the marriage is one of the most striking in car assembly. The painted body shell is lifted slightly above the moving chassis assembly by a synchronized hoist system. As the chassis slides into position beneath the body, the two are lowered together, and a team quickly secures them with precision fasteners. At this point, the car's major structural integration is complete. The engine and drivetrain are physically connected to the body. Once married, the vehicle moves to stations where cooling lines, fuel lines, and electrical connections between the body and chassis are linked. This requires careful attention to routing, sealing, and securing. Every hose clamp, connector, and grommet is placed to avoid chafing or leaks, as even a small oversight here could lead to operational failures after delivery. The next focus is glazing, the installation of windows and windshields. Modern automotive glass is bonded to the body using high-strength urethane adhesives, which not only hold the glass in place, but also contribute to the vehicle's structural rigidity and crash performance. Before installation, the glass edges are treated for adhesion, and the body's window frames are cleaned and primed. Robotic applicators or skilled technicians lay a precise bead of adhesive, and the glass is positioned using vacuum lifters to avoid direct handling. Proper curing of this adhesive is critical, and vehicles are timed through the assembly process so that the bond sets before the car experiences any structural flex. After the glass is fitted, exterior trim pieces are added. These can include weather strips, side moldings, roof rails, and badging. The fit and finish of these components are critical to the car's perceived quality. Misaligned trim can create wind noise or water ingress, while inconsistent badging undermines visual symmetry. The doors, which may have been removed earlier for easier access during interior work, are now reattached. They are hung on hinges that allow for fine adjustment, ensuring consistent panel gaps and smooth operation. Once aligned, the doors receive their inner panels, window regulators, locks, and wiring for power accessories. The tailgate or trunk lid undergoes a similar process, with alignment checked to within millimeter tolerances. As the car progresses down the line, more systems come online. Fluids are filled: engine oil, transmission fluid, coolant, brake fluid, power steering fluid, and windshield washer solution. In many plants, these filling systems are automated to ensure precise volumes and to reduce spillage. The first electrical power-up occurs at this stage, allowing the vehicle's onboard computer systems to initialize. This is the moment where workers can begin testing electrical functions like lighting, wipers, and infotainment displays. Once the newly assembled Suzuki approaches the end of the main assembly conveyor, the atmosphere in the plant shifts from a building process to one of verification and fine-tuning. This is the beginning of the commissioning stage, where the focus moves from installing components to ensuring that everything functions exactly as intended. The car is no longer just a collection of parts. It is a complete vehicle that must now prove itself ready for the road. The first stop after major assembly is often the wheel alignment station. Here, the vehicle is placed on a set of precision plates and laser-guided measurement systems that check the angle of each wheel relative to the chassis and to one another. Proper alignment is critical for handling stability, tire wear, and driver safety. Adjustments are made using specialized tools that tweak the suspension's camber, caster, and toe settings until the readings fall within strict tolerances defined by Suzuki's engineering specifications. This step also ensures that the steering wheel will be centered when the car is driven in a straight line, preventing an issue that would be instantly noticed by a new owner. Following alignment, the car moves to the fluid check and topping station. Although fluids have already been added during earlier stages, they are now checked for correct levels and quality. any air bubbles in hydraulic systems, such as the brakes or clutch, are purged through a process known as bleeding, ensuring consistent performance. Coolant systems are pressure tested to confirm there are no leaks, and the fuel system is primed and checked for tightness to avoid vapor or liquid escapes. Each of these checks is both a safety measure and a warranty safeguard, as fluid leaks can lead to early vehicle failures. Now comes one of the most anticipated moments in the factory: the first engine start. At a dedicated station, the technician inserts the ignition key or engages the start button, bringing the Suzuki's engine to life for the first time. This is not a ceremonial step, but a critical diagnostic event. As the engine runs, technicians listen for abnormal sounds, check for warning lights on the instrument cluster, and monitor the readouts from diagnostic equipment connected to the vehicle's onboard computer. The engine control unit records any fault codes during the first start, and these must be addressed immediately before the car can progress. This step also ensures that fuel delivery, ignition timing, idle control, and emission systems are functioning properly from the outset. Once the initial engine check is complete, the car enters what is called the rolling road test. This is essentially a dynamometer station built into the assembly line. The vehicle is driven onto large rollers, which allow the wheels to spin as though the car were traveling down an actual road. The technician operates the vehicle through various speeds and loads, while sensors measure engine output, drivetrain smoothness, and braking performance. Onboard equipment also checks that gear shifts are smooth in both manual and automatic transmissions, that traction control engages correctly, and that the ABS activates as designed during simulated stops. For hybrid or electric Suzuki models, the rolling road test verifies battery performance and regenerative braking operation as well. After this dynamic evaluation, the car undergoes an emissions test. The exhaust gases are captured in a sealed system connected to high-precision analyzers that measure the concentration of pollutants such as carbon monoxide, hydrocarbons, and nitrogen oxides. The results must comply with the regulations of the market where the vehicle will be sold. If any parameter is out of range, adjustments to the engine management software or mechanical repairs are made immediately. Emissions compliance is one of the most heavily regulated aspects of vehicle production, and no car can leave the factory without passing this check. With the mechanical and electronic systems validated, attention turns to the finishing area. This is where skilled technicians examine the entire vehicle for fit and finish issues. The car is inspected under bright lighting and from multiple angles to detect paint blemishes, uneven panel gaps, or imperfections in trim alignment. Special gauges are sometimes used to measure panel gaps to within fractions of a millimeter, ensuring consistency from one vehicle to the next. In addition to visual checks, technicians test all customer-facing features. Every switch, button, knob, and lever is operated to confirm proper function. Windows are raised and lowered, mirrors adjusted, wipers cycled, and climate control systems run through heating and cooling modes. Infotainment systems are powered up to verify screen clarity, touch sensitivity, and speaker output. Even less obvious features, like seat height adjusters and child safety locks, are tested to avoid customer dissatisfaction. The underbody of the car is also inspected at this stage, typically with the vehicle lifted on a hoist. Inspectors look for fluid leaks, loose fasteners, or improperly routed cables and hoses. Protective coatings applied to resist corrosion are checked for completeness, especially around weld seams and in wheel wells where road spray is most intense. Once all systems are confirmed, the car enters the water test booth. This is an enclosed chamber equipped with high-pressure spray nozzles that douse the vehicle from every direction for several minutes, simulating heavy rainfall and splash conditions. After the soaking, technicians climb inside to check for any water ingress around doors, windows, or the trunk area. Sealing defects are corrected immediately, as water intrusion can lead to electrical failures and interior damage over time. If the car passes all these stages, it proceeds to the final audit line. This is often staffed by some of the most experienced personnel in the factory, as they perform a comprehensive review of the vehicle. The final audit is essentially a condensed version of all earlier checks combined into a single process. It includes visual inspection, functional testing, and a short, low-speed road test within the plant grounds. Any fault, no matter how minor, is documented and corrected before the car can be released. Once signed off, the vehicle's identification and tracking information in the production database are updated to reflect that it has cleared manufacturing. Protective coverings are then applied to vulnerable areas like the hood, roof, and interior surfaces to prevent damage during transport. From here, the Suzuki moves into the dispatch yard where cars are grouped according to their destination markets. Some are loaded onto specialized car transport trucks, while others are driven onto railway wagons designed for vehicle shipment. For export markets, vehicles are often taken to a port facility where they are driven into large car carriers, ocean-going ships with multiple decks capable of holding thousands of cars. Throughout this entire process, Suzuki's production philosophy emphasizes continuous improvement. Every issue found during assembly or final inspection is logged in a central system, allowing engineering and quality teams to analyze trends and implement corrective measures. This feedback loop ensures that problems are addressed at their source rather than repeatedly corrected downstream. Once a Suzuki car has passed its final factory inspection and been fitted with protective coverings, its story shifts from manufacturing to logistics. This is a crucial and often underappreciated stage because even the most perfectly built vehicle must arrive at its final destination without damage, delay, or compliance issues. The dispatch yard of a Suzuki plant operates with the same precision as the assembly line itself, ensuring that each vehicle is correctly identified, grouped, and routed toward the market it is intended for. Vehicles are scanned into a tracking system using their vehicle identification number, or VIN, which serves as a unique fingerprint for each car. The VIN is tied to the car's exact configuration, model, trim level, color, engine type, and any special market-specific features. This tracking system communicates directly with Suzuki's global distribution network, allowing logistics planners to match production output to regional demand forecasts. The cars are arranged in neat rows within the yard, typically grouped by destination, so that loading can be performed efficiently. For domestic markets, the vehicles are usually transported by specialized car carrier trucks. These trucks are designed with hydraulic ramps that can be adjusted to accommodate multiple rows of vehicles, often up to 8 or 9 depending on size. Drivers are trained in securing the cars with wheel straps or chocks to prevent movement during transit. The loading sequence is carefully planned so that the first vehicles to be delivered are loaded last, minimizing handling at intermediate stops. For longer distances within the same country, rail transport is sometimes preferred. Trains can carry hundreds of vehicles in enclosed rail cars, protecting them from weather and debris. The loading process involves carefully driving each Suzuki up narrow ramps and into the railcar bays, with only centimeters of clearance on each side. Drivers in this operation are trained to maintain extremely slow, steady movement to avoid any accidental scrapes. The railcars are then sealed until they reach the unloading terminal, often located near major distribution centers. When cars are destined for international markets, the process becomes more complex. Export-bound Suzukis are loaded onto massive ocean-going vessels known as roll-on/roll-off ships, or ROROS. These ships function like floating parking garages, with multiple decks connected by internal ramps. Vehicles are driven aboard under their own power and parked in tight formation. with only enough space for mirrors and doors to avoid contact. Crews secure each car with wheel chocks and lashings to keep them stable during the voyage. Depending on the route, these ships can carry thousands of vehicles at once, stopping at several ports before reaching their final destinations. The voyage can last anywhere from a few days to several weeks, depending on the distance between the plant and the destination port. During this time, the vehicles remain sealed and untouched with their protective films and coverings intact. Because environmental conditions at sea can vary, including salt-laden air, the factory-applied coatings and transport wraps are specifically chosen to prevent corrosion or cosmetic damage. Once the ship reaches its destination port, a highly coordinated unloading operation begins. Teams of trained port drivers board the ship and drive the cars off in a continuous flow, following a pre-planned sequence. The cars are then parked in secure port storage yards, where customs clearance procedures are initiated. Every country has its own import regulations, and Suzuki's logistics team ensures that each vehicle's documentation, including emission certificates, safety compliance paperwork, and shipping manifests, is complete and accurate before customs inspection. After clearing customs, the vehicles are typically sent to a regional distribution center. Here, a process called pre-delivery inspection, or PDI, takes place. Although the car has already been tested extensively at the factory, the PDI ensures that nothing has changed during transport. Trained technicians remove protective coverings, inspect the bodywork for any transit-related damage, check all fluid levels, and verify that the battery is fully charged. Tires are inspected for correct pressure, and software updates may be installed if newer calibration files have been released since the car left the factory. This is also where market-specific adjustments are made. For example, vehicles shipped to countries with different lighting regulations might have headlight aim adjusted or daytime running lights enabled or disabled according to local laws. Navigation systems are loaded with the correct regional maps, and owner's manuals in the appropriate language are placed in the glove compartment. If a dealer has ordered optional accessories such as roof racks, spoilers, or upgraded infotainment units, these may be installed at the distribution center to avoid slowing down the main assembly line. Once PDI is complete, the cars are released for final transport to dealerships. Depending on geography, this may involve another short truck journey or additional rail transit. Dealers receive advance notice of incoming stock through Suzuki's dealer management system, allowing them to prepare showroom space and schedule customer handovers for pre-sold vehicles. When the cars arrive at the dealership, the process takes on a more personal dimension. Dealership staff conduct their own incoming inspection to confirm that the car is in perfect condition. Any final detailing, such as washing, waxing, or vacuuming, is performed to ensure a showroom-ready presentation. Paper floor mats, seat covers, and steering wheel protectors are removed, revealing the untouched interior. If the vehicle is destined for immediate delivery to a customer, the dealership staff will carry out the handover procedure. This involves explaining the car's features, demonstrating controls, and answering any questions the customer might have about operation or maintenance. The VIN is registered in the dealership system along with the customer's details, marking the official start of the warranty period. From the customer's perspective, the journey begins the moment they take the keys. From the factory's perspective, however, the cycle never truly ends. Feedback from dealerships about customer experiences, warranty claims, and any recurring issues flows back to Suzuki's engineering and manufacturing teams. This closed-loop communication helps identify opportunities for product improvements, process refinements, and supplier quality enhancements. Interestingly, the logistics chain is also part of Suzuki's environmental strategy. Modern vehicle transport planning aims to minimize unnecessary mileage and fuel use, sometimes even consolidating shipments from multiple manufacturers onto the same vessel or rail line to reduce emissions. In some markets, Suzuki works with dealerships to arrange bulk deliveries that reduce the number of trips and associated carbon footprint. In global terms, the distribution network is as critical to Suzuki's reputation as the production line itself. A flawless manufacturing process can be undermined by mishandled shipping, customs delays, or damage in transit. This is why Suzuki invests heavily in both technology and training to ensure that from the moment a vehicle leaves the assembly line until it arrives in the customer's driveway, it remains in the same pristine condition it was in at the final factory inspection. While the sight of finished Suzuki vehicles streaming out of the plant toward dealers and customers is the most visible sign of success, the real heartbeat of the company's manufacturing prowess lies in what happens behind the scenes. The precision of assembly, the timing of parts deliveries, and the consistency of quality all trace back to an intricate web of engineering coordination, supply chain management, and production system design. This interconnected system is what allows Suzuki to produce vehicles in large volumes without sacrificing the meticulous detail that defines a well-made car. The cycle begins long before the first sheet of steel is pressed, with engineering teams designing every component to be not only functional but manufacturable. This is known as design for manufacturability, or DFM. The aim is to ensure that parts can be produced consistently at the right tolerances and installed efficiently on the assembly line. For instance, a bracket might be designed with built-in alignment features that allow it to snap into place in only one orientation, eliminating the possibility of incorrect installation. Even the routing of a wiring harness is planned to minimize the number of bends and attachment points, reducing both assembly time and the risk of damage. This level of planning requires intense collaboration between product design engineers, manufacturing engineers, and even supplier representatives. Suppliers are involved early in the process to provide feedback on material selection, forming methods, and cost implications. A headlight supplier, for example, might work directly with Suzuki's styling team to adapt a design so that it can be assembled with fewer screws or clips, speeding up installation on the trim line. These interactions happen months, often years, before a model reaches production. Once the design is frozen, Suzuki's manufacturing engineers turn their attention to the factory itself. Every model introduction requires a detailed assessment of the production line layout, tooling, and automation requirements. This might involve installing new welding jigs for body panels, programming robots for different spray patterns in the paint shop, or creating custom assembly fixtures for unique components. Retooling a line is a massive undertaking, often done during scheduled downtime, to avoid disrupting ongoing production of existing models. One of the most critical decisions at this stage is determining the level of automation versus manual labor for each process. Suzuki, like many automakers, uses robots extensively for operations that demand absolute consistency, such as spot welding, seam sealing, and paint application. Robots excel at repetitive, high-precision tasks, and their ability to work in hazardous environments, like the fumes of a paint booth, improves worker safety. However, there are many tasks where human skill remains unmatched. Complex interior installations, final fit adjustments, and quality inspections often rely on trained technicians whose judgment and dexterity can adapt to small variations. For example, adjusting a door to achieve a perfect gap relative to the body involves subtle manipulation that a robot cannot yet match with the same flexibility. Suzuki's philosophy tends to blend automation with human oversight, creating hybrid workstations where robots perform the heavy lifting and humans ensure the final finesse. To keep everything running smoothly, Suzuki employs just-in-time manufacturing principles. This means parts arrive at the assembly line precisely when needed, rather than being stockpiled in large quantities. The benefit is reduced inventory costs and the ability to respond quickly to changes in demand. But this also requires a flawless supply chain, where every supplier delivers exactly on schedule. Any delay, whether from a parts plant, a transportation breakdown, or a customs holdup, can halt the entire assembly line within hours. To mitigate this, Suzuki maintains contingency plans and sometimes dual sources critical components so that production is less vulnerable to disruptions. The flow of materials within the factory is another area of intense engineering attention. Components are often delivered in sequenced racks, arranged in the exact order they will be installed. This eliminates the need for workers to search for the correct part, shaving seconds off each installation and reducing the risk of mistakes. In high-volume areas like the trim line, these seconds add up to major efficiency gains over the course of a day. Information flow is just as important as material flow. The entire production line is governed by a manufacturing execution system that tracks each vehicle in real time. As a body shell enters the assembly line, its VIN is scanned and its build sheet is instantly displayed, just improvements, no matter how small. A simple change in the shape of a parts bin or the angle of a work platform can reduce strain, prevent errors, or shave time from a process. These changes are documented, evaluated, and, if effective, standardized across the production line. Quality control is embedded at every stage, not just at the end. Inline inspection stations use laser scanners, vision systems, and torque sensors to verify that parts are installed correctly and that critical dimensions are within tolerance. If a defect is found, the car can be diverted to an offline repair bay for immediate correction. This prevents issues from traveling further down the line where they would be more difficult and costly to fix. Equally important is the feedback loop between manufacturing and product engineering. When recurring assembly difficulties or component defects are identified, this information is relayed back to the design teams. They can then modify the design or manufacturing process to prevent the issue in future builds. For example, if a clip securing a wiring harness is found to be difficult to engage consistently, the design might be altered to make it more forgiving during installation. In essence, Suzuki's manufacturing ecosystem is a continuous conversation between design, production, and logistics. Each element shapes and supports the others, creating a tightly knit system capable of turning raw materials into road-ready cars at scale. It is this deep integration that allows Suzuki to maintain both cost efficiency and the reliability that customers expect.